Testing 1 2. Testing 1 2. Testing 1 2. Testing 1 2.
Yes. Do you want me talking? Or do you want to talk? Yes. Do you want me talking? Or do you want to talk? I guess that answers that question with the 7-second delay. I got it now. You happy? Question mark? All right, this is a final sound check for you, Nick. 3, 2, 1, sound check. 3, 2.
Good morning. This is Nick Hampshire. We'll probably start off the conference around 8:10. Give people some time to join us. So we'll be touching base every couple of minutes just to let people know. But we'll be starting around 8:10. Good morning. The time's 8 o'clock. We're going to probably get started with our welcome in about 10 minutes or so, give more people time to join us. Again, thank you for joining us this morning. Looks like we already have a pretty good number, so we'll just give a few more minutes for people to come, and then we'll go ahead and get started. We'll get started here in about 5 minutes. 5 minutes to go. All right, good morning. This is Nick Hampshire. Over here in New Braunfels, Texas, we're going to get started with our conference. If anyone good morning. This is Nick Hampshire. Over here in New Braunfels, Texas, we're going to get started with our conference. I forgot I had to mute the YouTube, so there's no there's no feedback. So hopefully that'll get started. That was a good sound test for me that the that the YouTube was working. So that was a good sound test. So again, my name's Nick Hampshire. Welcome to the 2020 virtual Texas Weather Conference. It's been a long time coming. We were supposed to have this conference in the spring in Lubbock, Texas, but COVID happened, and we had to postpone till September, and now the postponement turned into a virtual conference. There's been a lot of work behind the scenes to ensure that this conference would go on hopefully without a hitch. So I just want to go real quickly thank our committee members. As you can see here on the page, a lot of folks put in a lot of hard work to get this conference to happen. So everyone here I would like to personally thank for the work that went on. So we're not done with Lubbock. Our goal is to get back to Lubbock. Hopefully we'll be able to do that in the spring of 2022, considering everything is back to normal. So a couple of logistics issues that I want to go over. So you'll see the chat. Everyone sees the chat a little bit in the already. There's already some chats going, some banter going on. That's where we're going to have the Q&A portion of the conference. The Google Meet's only going to be for the person presenting at the time. You can see Patricia is already in our Google Meet, and so the chat questions. That's where we want to see the questions, and then I'll pass those on directly to the presenter, and we'll go from there. We ask that you have some patience. A lot of testing went on behind the scenes to ensure that things would run smoothly. For those in Southern Region, I am in the office on the Southern Region Wi-Fi, streaming this to the YouTube. So you know how that can go sometimes. So hopefully we have a good internet connection and so forth. If for some reason the internet does drop out and the stream the stream ends, just go back to that YouTube link, refresh it, and there should be another new stream for you to click on that home page on our YouTube channel. The same thing will be after lunch. On our lunch break, I'm going to shut down the stream, and then after lunch, it'll be a new stream. So just go to that home page again and click on our live feed there on our home page. So hopefully things go on without a hitch. I expect it to, but you never know with internet and technology and things like that. So we just ask that you have some patience if things do go a little squirrely. So with that, Patricia, if you want to kick off our conference, our 2020 virtual conference, we have Patricia Sanchez with the National Weather Service in Fort Worth. Our session 1 is going to be providing weather information, so she's going to kick that off with a presentation titled Supporting the National Weather Service Mission with ArcGIS Applications.
Thank you so much, Nick. Good morning, everybody. Being the first one is definitely you can make all the mistakes and then hopefully the next person will be able to you fix it. So that's a great start. But I'm really excited to present, and hopefully everything will go smooth. So we'll go ahead and I'll present now my screen. And then we'll go ahead and start real quick. And hopefully you can see my screen on the presentation now. And then, like Nick said, I'm going to be talking about the ArcGIS applications and the use of for us in National Weather Service, especially for us here in the Fort Worth, Dallas local office here. I've been a meteorologist for a little bit over 3 years. Started working with ArcGIS applications probably in the last 2 years. It's still been a roller coaster, learning a lot, but it's probably, you probably heard in the past, is really exciting to be using these tools to do our work, to kind of support our mission. So we'll go ahead, we'll start it here with why is it useful? Why GIS is useful for us at the National Weather Service. And, you know, GIS, you probably heard it at some point, and now it's been more popular because, you know, with all the technology changing and all the tools are out there for us to provide our mission. So the GIS combines power visualization and analysis. It gets the mapping and the analysis together. And then we're using specifically the ArcGIS developed by Esri, the National Weather Service, and NOAA had this license for, you know, several years. And then, you know, slowly we're getting application to use this in our, you know, meeting the partner request and then telling what we need to tell the people out there. So it's kind of like that other tool in our toolbox there to provide and support our mission. And, you know, why is it important? You know, we think, you know, we wanted to keep enhancing the awareness. We need to hopefully reduce the vulnerability in our area, in our communities. And of course, keeping up with the demand. You know, the technology keeps growing. You know, everybody has a phone, everybody can access that data in a phone. So we need to provide a little bit more than that. We go back from having a presentation, a PowerPoint presentation that is, you know, really useful. You know, if you go do a talk out there, you know, as a static, you know, you do your presentation and that's done, right? But now, you know, we're with all this sources of information and all this pieces of the puzzle, trying to put it together. What about, you know, you're using the cloud, you know, we have all that data already available out there. So we're using kind of having this ArcGIS application to kind of present the same information in a different way and hopefully, you know, meet our mission and kind of like help to continue our mission out there. So like I say, you know, the NOAA, we are, you know, under the NOAA Geo platform is the, you know, the source out there for us as the National Weather Service. But again, this goes bigger. Everybody across NOAA has, you know, the opportunity to use this data and maps and analysis. And it's been using for, you know, several years to incorporating these tools. We're using it specifically ArcGIS online and ArcGIS software because the online part gives us the opportunity to have it, you know, interactive out there that doesn't need to be physically in a computer. So if you take a look around, there's probably so many stories, maps, dashboards, briefing page analysis, etc. across just within our agency. It's been growing since the last couple of years. A lot of people are taking and making this a really, you know, very important task because again, it gives us that flexibility to have that all the data that we already have available out there in a different way and just probably in just one area and one space there. So in our local office, we started working in probably the last couple of years, and we use it for a couple things. We're still growing, we're still learning as an office and as a staff and as a team. And then we use it for a couple things, like I said, situational awareness, conference calls, self-briefing, analyses, and even 4-minute analysis. So we're going to talk a little bit about all those and show you guys how it looks for our different themes and our different subjects. So we're going to start right away with the situational analysis, situational awareness display. This is for us an internal dashboard or story maps, people call it. So then we have a bunch of information there right at the fingertip of the staff. We have it there in our situational display in our office. Sometimes, you know, you can actually open it at home when you're teleworking. So this gives us just one shop or one stop for all the information that we need. You know, for example, here we have our operation levels, the calendars. We can have, you know, the thunderstorm outlooks, aviation, you know, rivers and QPF and all this information that the staff would want just in one area here. And then another example here with the flooding potential. You know, we have the flood potential for each day. So this is kind of like a neat way to have everything in just one location. So you can take a look today, tomorrow, day 3, and then the whole thing in just one area right there. And it auto updates. I don't have to go back and clip the picture from the WPC and then put it here. It's already going to be embedded in the same map. So it's really, really cool. And then one of the other examples here that I show is, we have the operational plans. Let's say that we have a severe weather going on, a winter weather going on, and we have our operation planning worksheet. This is where people are going to be seated, or this is what the duties are going to be assigned. So all this is there embedded. So if you're home, you can take a look who's sitting where, who's doing what, and then this is going to be updated as the staff updates at the office. So this is kind of like a great way to kind of have everything, like I said, in at least for our staff internal briefing. So we keep adding this. We do have kind of, for COVID-19, we have hospitals there. So this is kind of like a different awareness display that we use in our office. So next, we start working on the self-briefing conference calls project last year. Of course, probably a lot of offices have conference calls during different types of events. And specifically for us during winter weather, that doesn't happen very often. I'm glad. Definitely, to give us another challenge. How do we do these conference calls with the latest updates, with the latest information there? The staff will have to prepare how many of those we do. So we created these dashboards for our partners that they can have every single tab there with the information just concentrate, or the staff can just concentrate on the topics. What do we want it to say? The talking points. So the forecaster, the staff will only update these two tabs right here, and then done. You just have to save it, and then it's click, and the partners will have this, and then the conference call, they can just focus on actually answering them questions and stuff like that. So instead of trying to spending the time cropping and getting all the information, this is right there. So I'll show you real quick. How does it look? So this one right here, this is the same. They can click and take a look at the temperature. They can take a look at the different information. And the other tabs, they can click on the forecast. They can click the hourly forecast for example, here for each independent school district. So they can click and get that information specifically for that location. And again, this is all the information we already have in our website. It's just to have everything in just one location, which it makes it really, really good and really useful for us. So the next step we're going to show real quick is the story maps. We do have stories that we also that possibility to share and tell a story about that. So this was our top weather events of last year. We kind of had a summary of our biggest, kind of more significant weather events during the year. So that gives like a really nice interactive summary that people can click, can view, can access that data. They can click at tornadoes, what was the tornado, what was the information, what was the path, kind of like going back to the science and kind of merging the science and the technology in one step. Right here, we were able to get the radar loop and show it right there for like this big hail event. So it kind of gives us like a nice way to summarize our event. So this can be done, for every event, or this was just an example for us for last year. So hopefully we'll continue to work on this, because again, this gives like a really nice to kind of builds out all the technology together for us. So this is really, really nice. So next, the last but not least, we use ArcGIS Survey 123. There's another application under ArcGIS. And what's cool about it is, it's another way to create informed data collection, assessment, survey. And for us, the National Weather Service here in Fort Worth, we needed to get some partner comments and assessment for weather thresholds that we were going to use. Our office is going to start using weather matrix for specific DSS events, but we needed to actually get what are going to be our default values. So we needed to ask our partners, what do we need? What are going to be the default values? Is it going to be temperature of 32? Is it going to be winds of 20 miles per hour? Is that going to be okay? That's going to be like a red flag. So all that information we needed from our partners here across North and Central Texas, So we created this form, and we use server 1 to 3 because it's really nice to kind of automatically gives you a map where your results are. So you would know pretty much where those locations were from, and right there at your fingertips. So it kind of gets that analysis right there. We were able to kind of tabulate it. It has graphics already there. So it's kind of like that location part that sometimes is important. Do we have a really good data from different locations? So we had cover North and Central Texas. So this was a really good way to kind of start testing this here in our local office to see what else can be helpful for us to do our work easier, our job easier here. And we know, other National Weather Service offices have texted the survey 1, 2, 3 for damage surveys. So this is kind of growing now. So we're probably going to keep hearing and looking about this in the foreseeable future, because it really is a really nice way to have a geolocation in with your information that you want. So as a summary, really quick here, kind of have, the GIS technology is giving us that opportunity, is giving us this sharing ideas, and of course there's a challenge with it. But again, we just kind of working together for especially these times that we have teleworks. People are working from the office, from home. This kind of gives you that connection with another tool. So we have these are our ongoing and future projects. So we hopefully keep working on it. But yeah, this is we're excited to use this, and hopefully we could keep learning about it. So this is all I have. Thank you so much for your attention, and I'll take any questions.
Thanks, Patricia. We have one question or two questions. It looks like you might have answered one of them. But one question was, when looking at rainfall amounts for different cities, is it better to interpolate the data or to, and I might not be pronouncing this right, Krige, K-R-I-G-E, the data?
Okay, so I'm not super familiar with that. Yeah, with the last term that you said there. But what's technically, the layers, we have the QPF, we have the EROs for WPC, we have all that data already out there. And right now we're just showing it as simple as, grabbing those, just KMC or just files and put in our ArcGIS. From there, you can do anything. That's what's cool about it, that you can do analysis to your own particular interest or scientific research, or even for a day-to-day thing. Right now, we're just keeping it to use it for right straight from the WPC or from the NOAA Geo-Platform stuff. But again, yeah, that's possible. You can do analysis to pretty much as far as that you can think of, and have that coding or have that experience. Definitely is going to help.
Awesome, thank you. Awesome presentation. I think there's a lot of folks from different weather service offices that may be interested in what you're doing. I thought it looked really interesting. So far so good with the first presentation. I don't think there was any hitches. So Patricia, thanks. Feel free to drop off and join us on the YouTube. And again, you can look at the chat, and that question was in chat, and you may know what that word was. I was probably pronouncing it really poorly. But anyway, thanks, Patricia. Looks like Rick Mitchell has joined us. Hey, Rick, how are you doing?
Good. Nick, how are you?
Good. So if you want to go ahead and share your screen, and I'll introduce you. Rick Mitchell works at the NBC station in DFW. He's been there for quite some time now, and he's going to talk about the evolution of broadcast meteorology over the last 30 years and a sneak peek of the present and what's to come. So this should be a really interesting presentation. So with that, Rick, I'll leave it to you.
Are you seeing my screen? Oh, very good. Okay. First of all, good morning. Nice job, Patricia. It's always intimidating following Patricia, but I will do my best. My name's Rick Mitchell. I'm the chief meteorologist with NBC5 here in Dallas-Fort Worth. Been a weather geek my whole life. I've been a meteorologist for almost 33 years now, and a broadcast meteorologist for the last 30. And so I thought it'd be fun to kind of look back at this profession that I've enjoyed so much, and I've watched from a little kid, And let's just start at the beginning. The early years. Obviously, I wasn't around in 1948, but that's kind of the year that things really got going, where TV started. That's when our TV station started. And so for this first little bit, let's talk about those early years. And you can imagine all of a sudden you have this new medium, all right, and it's a way to reach some people, and from newspapers and radio. And then all of a sudden television comes along, and not many people really knew how to utilize it. The programs at first were very, they weren't very good. And there was one person, at least here in North Texas, that stood back and said, you know what? We need to have weather on this new thing called television. And that was Harold Taft. Harold was a meteorologist for American Airlines and happened to be working fairly close. He went to the station one time. At that time, it was WBAP. And he said, man, I could provide you weather. You pay me a little bit and I will provide you weather. So Harold was one of the first broadcast meteorologists in the nation. And he started, apparently he went on the air October 31st, so Halloween night of 1949, and worked at WBAP, and then eventually KXAS is what it is now, up until 1991. So he was a real stickler. He was insistent on science and not silliness. He was a lieutenant colonel in the Air Force Reserve. And in talking with my former chief meteorologist, David Finfrock, who worked with Harold, Harold liked things done a certain way, and certainly science was his way. Well, not everybody wanted to take that approach. In fact, the majority of other stations kind of chose a different style. They went more with a blend of entertainment over substance. And think about it. If you weren't a meteorologist, it was hard to get the scientific aspect of this. So you had to draw the viewers in using maybe puppets or drawing little cartoons and things of that nature. And then there's this, whatever this is. Hey, let's get ladies and we'll have them hold up the weather map. So early television weather was, I don't know if I want to say it was buffoonery, but it was certainly more entertainment driven than it was in terms of science. And early weathercasts, as you might imagine, they focused a lot on what already happened. Okay, they'd spend 5 minutes talking about the low temperatures from this morning or what is happening right now. There was very little forecast-driven properties to that early weathercast, which makes sense because the forecast, wasn't terribly reliable back in the 50s and the 60s. And the forecast itself only went out a couple of days. I think Harold Taft, the longest his forecast ever went out was a 3-day forecast. Well, from my personal perspective, that's when the 1970s came along. That's when I became more aware of what was going on. Okay. That's when I started paying attention to the weather. And I'm from Omaha, Nebraska. So let me give you a little background. In 1975, we had the blizzard of 75 in January. I was out of school for 5 days. It was glorious. And then we had the tornado of 75, EF4 tornado. So Omaha was a victim of a couple of huge weather events. By 1976, a new person came in onto the scene. His name was Charlie Martin, and he was the first television meteorologist at Channel 7. And man, I'll tell you what, I dug it, okay? I was totally into it because he brought credibility, all right? He was a meteorologist. He'd use his marker. He would draw on these maps. He'd explain to me, this area low pressure, yeah, it's going to be moving off to the northeast. And you know what that means? Snow for Omaha. So I thoroughly enjoyed his presentations, and I immediately disregarded anybody who was not a television meteorologist. So the 70s was kind of the dawn of more widespread meteorology. If you're a real geek, you might remember this. I don't know, you got to be a little bit on the old side, but do you remember AM weather? Okay, that was on PBS, and there was, every day at 6:45 during the week. I remember getting ready for school and I would have AM weather on. It was no personality, but a lot of good information. And it kind of set the tone for, hey, we can do this seriously. All right. So now we transition from the 70s into the 80s. And what happened in the 80s? Bam, local on the 8s. The Weather Channel started. Cable TV is expanding. More advanced television weather graphics. You saw stations getting away from, hand drawing maps or using markers. Now they're starting to use computer graphics systems. But still, at that point, a lot of the folks depended on their local television meteorologist to get their forecast. I used a weather radio and I would call into the Weather Service recording phone line. That's what weather geeks do. The 90s brought me, not that that's a big deal, but it is text computer made by Kavoris. And yes, I had to hand draw each one of those temperature bands you see behind me. So the 90s brought that, but still most people are getting their forecast from local TV. We still kind of had this monopoly. Yes, radio and some cable, but cable really hadn't exploded yet. But the revolution was about to get going because something was lurking on the horizon. And I'm sure you can guess what it was. Yes, this thing we call the information superhighway. The internet all of a sudden is introduced and it becomes more and more widespread. And that certainly was a game changer. I remember in the late 90s thinking and asking, what does this mean? Are we going to actually have a website? Are we going to put our forecast? Will we put our forecast on the actual website? So the explosion of the internet, the expansion of cable TV, that brought the new landscape to the area. But really, the biggest, most revolutionary change was what? Yeah, the smartphone. What was it? 2006, 7, 8, something like that, when we got our first iPhone. And with that, obviously became weather apps. And so now we've reached the point in the 2000s where all of a sudden people don't need Rick Mitchell anymore. They have weather, they have radar right in the palm of their hands. TV, oh, that's a dinosaur. So, there are more ways than ever to get a detailed local forecast. Now, granted, I think the majority of the apps are junk, but the general public doesn't necessarily know that. So they're getting their weather, they have their radar, they're tuning into their favorite Facebook meteorologist who's 14 years old. Are broadcast meteorologists even needed anymore? What do I say to the young people coming up? Well, I think yes, the answer is yes. But our role has certainly evolved over what it was when I first started, or certainly when, Harold Taft got this whole thing rolling. We have to be better than the apps, okay? Each day I approach my forecast knowing that the majority of my viewers already know the forecast. So I have to bring something special. I have to provide my take on the forecast. I know the app says this, but what does Rick say? That's what I am striving for, that they will say that. We have to be local severe weather experts, somebody that they're going to turn to when the sky is dark. We have to be science communicators, okay? We have to break down the things that are hard and make them easy, not just weather, but all science. And we have to be a trusted weather source. People have to be able to trust what we're saying. And we can use new technologies such as augmented reality at the station to make it easier. Hey, why say something in 2D when you can do it in 3D? So in other words, we have to go beyond just giving the forecast. Because remember, they pretty much already know the forecast, but we want them to get it from us. And then there's this new twist. We got this COVID thing going on. And now all of a sudden, we're working from home. My back patio is my studio. I never thought in a million years I would be broadcasting from home. But it's not a negative thing. Working from home has brought opportunities. Viewers see us as real people. And instead of them inviting us into their homes, we're now inviting them into our homes. It gives us a different perspective. It gives us a chance to form a stronger bond. My viewers know my dogs. They know that my wife likes to decorate for Halloween. Okay. We can still provide informative and educational content. We can just do it in a more casual setting, I guess. Okay. So what's next? Well, I struggled with this one. I don't know what's next. I know that if you look at this positively, you can say that the ability to reach our viewers is going to be much higher than it ever has been before. Streaming services, TV station apps, social media. The opportunities are there to reach out and grab your viewers and make a connection. Yes, they're being pulled in several different directions, but it's going to be up to you or us to be creative enough, to be smart enough to give them the information that they're craving, even if they don't know that they need the information. Maybe they don't know that they want to learn about the Coriolis effect, but we're going to explain it and they're going to go, you know what? That's pretty cool. I like watching this person. So that's my take on this. I hope you enjoyed it. Let me know if you have any questions, and I appreciate the opportunity to present today.
Yeah, Rick, that was a really good presentation. I really enjoyed the parts about what you can do that the apps can't do. And one quick anecdote is I grew up in Southeast Texas. Greg Bostwick, I don't know if you know that name in Beaumont, but those folks down there trust him for over anything when it comes to hurricanes. Even my own mom will listen to Greg Bostwick over what I say. So he's kind of built that down there, that trust. A couple
That's
of questions.
Great, and that's what we want.
Yeah,
that's exactly what, as broadcast meteorologists, we have to strive for.
And he does that through science too. So
yeah.
A couple of questions in the chat. We have one. Can you comment on the role of the broadcast Met during live and ongoing severe weather events?
Well, it's funny because one of the things that I think has changed, in some ways, the broadcast Met has become somewhat of a counselor, I think, because so many people are frightened by storms. And I look at it as, it's our role to give the information and give it, with extreme accuracy as best that we can. And we're taking that information from our partners at the National Weather Service and giving that information so that the viewers can make the decisions that they need to make. But it's also important that we do it in a way that we're not freaking everybody out. When the sky is dark and the sirens are sounding, even keel. I see a lot of, things, a lot of examples where Mets might get a little high strung and, they're yelling and this. No, you got to stay on an even keel. I think that's what I feel like my responsibility is during severe weather coverage.
And then lastly, one quick question. When the social distancing rules are relaxed, do you see the remote broadcasting from home continuing at all, or will it be all hands back on deck in the studio?
That's a great question, and I have that same question. I think we've entered a new era now that, yeah, I think eventually we will go back and we'll do things from the studio, obviously. But I also think that the opportunity is there for people to work from home if need be. Think about it. If there's a blizzard coming, remember when we used to have snow in North Texas? Instead of the station renting hotel rooms for us by the station, we could stay at home and provide that information. Maybe we could do holiday work from home. Maybe we could have work at home Friday. I don't know, but I think now that the box has been opened, I don't think it will ever be completely closed on remote broadcasting.
Those are all very good points. I think the whole industry across the United States probably will be changed forever with working from home.
I think so.
That was very good. We thank you for joining us again this year. I think a lot of people got a lot of useful information from that. So we thank you again.
Thanks, Nick.
Now joining us, looks like another working from home participant is Greg Waller from the West Gulf RFC. It looks like Rick should be ending. There you go. There you go, Greg. If you want to take over and present your screen while I introduce you. Greg Waller's worked at the West Gulf RFC for quite some time that he'll probably be able to share with you, but I know the number's big. He's going to be talking about enhancing the threat scale, how to adequately capture all the threats associated with tropical storms and hurricanes. So Greg, why don't you go ahead and take us on?
All right. Thank you, Nick. I want to apologize to everyone because one of the things I've always said is I need to stay in my lane. I need to stay in my lane. But this whole presentation is me getting so far out of my lane. I'm in the bar ditches on a couple of occasions. What's happened is over my 20 plus years here at the River Forecast Center, I've worked in the weather forecast office in San Angelo and Houston. So I'm pretty much a Texas meteorologist and hydrologist. But I hear certain phrases that kind of trigger a reaction. And what has ended up happening is our official National Weather Service, which is also the National Hurricane Policy, they used to do category Saffir-Simpson scale that had storm surge, but they realized there's so many variables that go in to creating storm surge and that they're not really representative of the strength of the storm. The Saffir-Simpson scale is a wind scale derivative storm, and everyone locks in, oh, it's a category 1. It's just a tropical storm. And we're finding out over time that there are multiple threats to every tropical event, and that would be storm surge. I call it the saltwater component. Inland flooding, which is where the weather forecast officers really dive in with the flash flood warnings, and then my office as a river forecast center, the freshwater component, and then there's also the wind component. There's also a tornado component and other things as well. But the point is, the official National Hurricane Center Saffir-Simpson scale is a wind-driven item, and I feel that we're not always adequately conveying the threat of the saltwater and the freshwater component. Now, I've been brainstorming around. I've been working on this for about a year and a half of what can we use that's existing out there. I don't want to create any new paradigms or color scales, but I want to grab what we're already using, and can we create an impact-based category system so that we're not going to say, hey, this is going to rain 10 inches, because 10 inches of rain in a flashy hilly area like the hill country is one thing. 10 inches of rain on the coast is one thing, and 10 inches of rain in Lubbock or Albuquerque is borderline unheard of. And how do you communicate 10 inches of rain? Well, let's communicate the flood impacts from that. What I want to do is I want to expand this. And what I was thinking is the other day, I was creating a file and I realized I didn't have proper commands in the Unix. And I just real quick, I knew it, changed the ownership with a 775 command. And I realized we have been trained over time with simple commands like that a series of numbers can mean read permission, write permission, execute permission, all that kind of stuff. Why can't we expand from a one number Saffir-Simpson scale to something more different? So why am I doing this? I have literally heard these statements either from fellow meteorologists or from friends and family in the last 2 years. It was just a tropical storm. I'm not going to worry about it. Okay. Well, what's the track? Well, we know the track is a skinny line, which is the center of circulation, but the impacts from a storm can go 100, 200, 300 miles away from the center. And I don't want anyone focusing on the track. I want them focusing on the impacts. It's barely a hurricane. This is a low end event, man. It's not even going to happen. It's just barely a hurricane. Or you know what? Tropicals, that's the coast. I don't live on the coast. I'm not going to be worried about it. We know the inland threat, especially from flash flooding and heavy rain and river flooding, extends, all across the United States in some cases. So by doing that, I really want to stress this. This is my tilting at windmills. We really got to lock in on the flood threat and how to convey the heavy rain messaging threat. Is routinely a larger life taker than tornadoes and then hurricanes. You can see heat there is significant as well. And we have National Weather Service weeks and environments to where we promote heat. We were trying to promote rip currents, but let's take this opportunity. We're going to focus on the floods. We're going to tie it into the hurricanes, and we're going to try to improve our messaging. So what I've done is I call it Safe for Work, which is your surge component, your flood component, and your wind component. Surge, the National Hurricane Center has breakpoints that they use for where they want to color code on some of their maps. Can I take the surge component? I'm not a surge forecaster. I'm a freshwater forecaster. So I don't want to recreate something. They've done a lot of social science on this matter. So I'm just going to grab what the Hurricane Center uses. The flood, the Weather Service already has an AHEP scale to where, we have, action stage, a minor flooding, a moderate, a major, and then record is easy to explain. What if we tied that into the existing Saffir-Simpson scale? So you can see a category 1 surge would be these values, a category 1 flood scale would be these categories and wind. So instead of just saying, hey, this is a category 3, if we're expecting surge of 3 to 6 feet, and this is going to bring moderate flooding with wind speeds of a Category 3 hurricane, it wouldn't be a 3 hurricane. Maybe it'd be a 2-3-3 hurricane. And then we would explain 2 means 3 to 6 feet. The 3 for flooding would be moderate flooding or greater, but we're not just locking into the wind scale. So as you break it down a little bit more, I borrowed the Hurricane Center surge height thresholds. There is wiggle room. They put out a range, and there's 4 levels here. Well, I needed 5. And what I heard a lot of emergency managers tie this into, and those can correct me if I'm wrong, but basically it's, when you get to a certain feet, like 6 inches to 3 feet, sometimes people can walk out, but 3 feet, you're going to need, maybe high-end trucks, high-end vehicles, high water vehicles. At 6 feet, 3 to 6 feet, maybe you're talking about boats and no longer having vehicles in there. 9 feet, boats may not even be it. You're maybe talking about, the bottom of your house, your roof, and you're now talking about helicopter rescues. So these aren't just random numbers. There are impacts tied to it from an emergency response view, but I'm like, hey, if these things exist, let's put them in let's create a 5th category and put them in a scale. With the Weather Service, it's easy to do AHAPs. You just remove the green, the river is behaving, and go action. It's high water, the river's high, and it could be issues. Everything in the River Forecast Center and the Weather Service, they're impact based. A river out of its banks is flooding, but we call it minor flooding when it starts to have impacts, secondary roads, parks, that types of thing. Moderate flooding is when you start threatening major roads and threatening buildings. Major flooding means there's water in buildings, and major highways and major roads are underwater, and record is easy. It's never been this high before. So the AHAP scale has pretty much a rough and ready 5-tiered system in there. And we can tie that in with the River Forecast Centers on this graphic so that, ignore the low flow drought, which unfortunately I will probably be predicting here in the not too distant future in Texas. But, the no flooding, but the 5 impact categories, action stage, minor, moderate, major, and record, that makes itself available to a 5-tiered system that exists for our current wind category. The Saffir-Simpson is a wind category. The Hurricane Center, their expertise is unmeasurable. They know what they're doing with it. Don't try to replace it. Build off of their expertise. And you can see that with a 5-tiered category system for the Saffir-Simpson wind scale, that we can tie in a 5-tiered flood system for storm surge and a 5-tiered river flood system or freshwater flood system. And I think there's some ability here to try to increase messaging the threat ahead of the storm. The research, I knew that had happened, but the research, I guess back in 2010 is when the Hurricane Center stopped having storm surge tied to the Saffir-Simpson wind scale, because the storm surge variables are not necessarily wind driven. There's so many other things in place. Well, the storm surge is a killer. Let's find a way to bring it back in. Okay, not a Saffir-Simpson scale, but something different. So I started grabbing examples this year, and wow, I did not expect Mother Nature to throw me so many examples. But right off the bat, we had Cristobal form in June. It's moving to the central Gulf Coast. It's going to be a tropical storm. And then I went to the River Forecast Center, Slidell, said, give me your messaging. What kind of flood threats are you messaging? And they said, oh, yeah, we're looking for minor to some moderate river flooding. So in this case, instead of saying it's just a tropical storm, we pulled a storm surge product that came out of the Hurricane Center, and they said 3 to 5 feet. We've got moderate river flooding and a tropical storm of 0. Instead of saying just a tropical storm, this would be a 2-3-0 storm. And if you want to really highlight it, maybe we say this is a 3 storm based on river flooding, but it's a 2-3-0 storm overall. I don't know how to convey that, but the point is I have now gone from just a wind field probable type of event to now I'm including that there is a storm surge threat and a river flood threat. When we went into Faye, this one really caused me some issues because it was moving fast. It was going into the Northeast. I reached out to our Northeast River Forecast Center briefing to find out what kind of flooding they were expecting. And with the fast moving storm and the rainfall amounts, they really weren't expecting a lot of river flooding. They expected a bunch of action stage and high criteria, but they didn't even want to lock onto that. And it was moving in such an area that the storm surge really, they're minor coastal flooding. They didn't even want to put, the Hurricane Center didn't even put values on it. So this is a case where, our tropical storm is moving in and there is no risk. And that right there creates a problem as a coordination hydrologist. There's always a risk. And I found out that maybe here's the fly in the ointment. And this is why I want to gather the experts from around the field, the emergency managers, the media, the fellows, scientists, the research scientists, try to figure out, is there something that we can do to try to enhance this threat? It was a fast-moving tropical storm, but it didn't pose a significant storm surge threat or river flood threat. So maybe a 000 storm would be the accurate way to portray it. Then came Hannah, where I had the ability to work both the meteorology shift at the River Forecast Center and all of the IDSS support for our office. And I realized Hannah coming in, the surge, it's fast, 3 to 5 feet, but we were expecting moderate river flooding in an area that didn't have a lot of rivers. And then, when it became a category 1, this is one of those things. It's like, do you tell everyone to focus on the category 1 wind speeds? No, this was a storm surge and a river flood event. And we were trying to hammer that home. And I actually heard from a Weather Service employee, I was kind of surprised by this being a low end storm. So if this is a Weather Service employee that knows the dangers of it, how are we portraying this information to the public that only tunes in, during the big events? And I felt maybe Hannah being a 2-3-1 storm means a little bit more than, it's just a category 1. We pull in Laura. Laura also clipped our area. This one had all sorts of parameters on it. Major hurricane category 4. That's a mistype there. It wasn't a category 1, it was a category 4, but it was moving fast enough. We had a lot of river flooding expected both in our area and the Slidell River Forecast Center, so we could lock into moderate. The flooding along the coast was storm surge related, and the values were off the charts. This was, catastrophic storm surge. This was a category 4 hurricane, but it was category 5 as for surge. So maybe 5, 3, 4, would that be a better way of trying to explain that Laura was more than just a wind speed thing? It had a storm surge component as well. And then, we were dealing with Sally. We knew Sally was going to be a rainer, but in this case, surge of 7 to 11 feet, major river flooding, but it was a category 1 hurricane. When I pulled this graphic, you say, it's just a category 1. Man, you better be hammering home the freshwater and the storm surge. So Sally is almost the perfect example of why I wanted to do this. Now, I've sat here this whole time and talked about river flooding and AHEPS graphics and storm surge and stuff like that, but I'm missing a component from the Weather Service, and that would be, what is the flash flood component? It is not a 5-tiered system, so that they do a none, a marginal, a slight, a moderate, or a high possible. The other thing is that it presented at the National Weather Association conference just a couple of weeks ago was this Flash Flood Severity Index tool. Now, it is a rating tool that's after the fact, kind of like an EF scale, and it would require a spin-up process across the nation to really gin it up. But what it is it tries to assign a category to the degree of flash flooding in an area, so that, a river, creek, or some crop, or a basement flooding, it's flooding and it's still severe, but it would only be minor. And then you go up to the vehicles and homes inundated with waters and bridge damage to a 3, to catastrophic, a Harvey type event, a 5. The issue with the flash flood severity index, again, it's based on the impacts that occurred after the fact. Do we find a way to meld that in? I don't know. I think that it's something, though, that we should consider. We either add a 4th category for flash flooding, or we find something to do that. In conclusion, I was asked to only speak for 12 minutes. Those that know me, I can speak to a brick wall for 12 minutes, but I hope I've got the point across. I want to get away from a 1-number Saffir-Simpson scale. That is a wind component only. Okay, and everyone takes into effect this is a wind component, and they sometimes don't grasp the concept of the other 2 really big life-threatening impacts from a storm, and that is the saltwater and the freshwater component. Many people die from the flooding. That's statistics. That's just life. That's the way it is. And they really don't matter if it's salty water, brackish water, or freshwater. They want to know how high is the water going to get, especially those along the coast. I wanted to find a way to include the storm surge threat back into a messaging system. And then I wanted to combine the inland flood threat, especially for those folks away that think, hey, I'm not on the coast, I don't have an issue. Right off the bat, I've been throwing this out to some of my friends, and they say 3 numbers are kind of confusing. I said, yes. What if I added a 4th, and that'd make it even more confusing? So do we add them all up? A 1, 2, 3 storm becomes a category 6. I said, oh yeah, if it was a 5, 5, 5 storm, that'd be a 15. And I thought that would be cool, right until I saw a tweet from Bojangles talking about a storm of spicy chicken goodness. It's a category 6. And while I'm thinking of fried chicken and how great that is, I see a lot of people in the weather Twitter, so to speak, rip into there's no such thing as a category 6. So I'm hesitant to combining these into 1 number, because I already know that there's going to be backlash that we'll have to overcome. And what I want to do is I want to find some way of evolving the message. That's my job as coordination hydrologist. But Rick and all the broadcast meteorologists here in the Dallas-Fort Worth area and across the West Gulf area, they are message amplifiers for us. The weather forecast offices and all the forecasters and the WCMs and the service hydros, they are weather amplifiers, message amplifiers for us. And I want to find some ways that we can try to take into account all of the threats of a tropical storm or a hurricane and try to improve getting the message out ahead of time to the public, and not just, oh, it's just a tropical storm or it's just a category 1 when we know there's so many other threats involved. So with that, that's some dude looks a lot like me that loves traveling the state of Texas, but I would be available for any questions. That's my contact information if you want to get in touch with me specifically.
Thanks, Greg. There's a couple questions in the chat, or 3 now, or 4. So it looks like you're pretty popular. You might just, for the interest of time, you want to just answer the questions in chat? Does that work for you?
Yes, sir. I will do that.
All right. Thanks a lot, Greg. Great presentation. Great idea. Looks like I said, you have a lot of interest there. So we'll see you. We'll see him in the chat. All right, now we have Lance Wood from NWS Houston. He's filling in for Sean Lukes, who's out on a fire as an IMET, and he's going to be giving a presentation on MinuteMets, Rapid Deployment of Meteorologists in Support of Emergency Incident Response. It's kind of fitting that Sean couldn't do this talk because he had to rapidly deploy to a fire. So go ahead, Lance, why don't you go ahead and take us away.
Sure, can you see it, Nick, the screen? Okay, great. Yeah, Sean Lukes is a senior forecaster at our office, and I definitely want to acknowledge Sean. This is his talk. He did the heavy lifting on this, and it is kind of ironic. He's deployed right now, and he loves it. So I'm glad he kind of got that opportunity to help out. But we'll talk a little bit more about Sean and other people at our office here. A clever title. That's Sean's idea there. I'm actually the Science and Operations Officer at the National Weather Service office. So the Texas City Y collision, I thought I would talk a little bit about this. This was a really big one for us, and still the biggest in my career as far as supporting a hazmat incident. And what's really interesting about this picture, this is the Summer Wind in front of you. That's that huge ship. It's over 500 feet long, but hiding in the fog over here is the real issue on the right side of the screen. That is an oil tank barge that basically got split there in the middle and caused this event. So what happened? Well, we released about 168,000 gallons of bunker fuel oil. And yeah, that wasn't hiding. And you can see it in this picture. It was right on the surface. We had to try to track this. It actually eventually left Galveston Bay and went offshore, and we tracked it offshore, and Corpus Christi WFO joined the fun with this. But this was a huge event, over 1,600 people at the incident command post, and we actually had 3 Mets covering this 16 hours a day for the first couple of weeks, and you see a couple of them there. And yeah, Houston's good at training people in decision support and hazmat, and then some of them have moved on, like Chris McKinney now runs decision support services for Southern Region, and Brian Kyle, still at our office, has a lot of expertise. He's a Marine focal point. He's really great with our Marine partners. Morgan's Point collision. So yeah, March is not a good month for us, right? So this is a year later, and we had another collision, and I was working with, I was the day shift that day, working with Melissa Huffman, who's now the warning coordination meteorologist at Corpus Christi, and she rapidly deployed. So we got notified of this collision around noon. It happened in the fog again, and she was there that afternoon, so providing support to the Coast Guard for quick cleanup effort, trying to get a handle on this one. And this was a different chemical. So now we have methyl tert butyl ether, which fortunately is a lighter kind of a gas blend. So some of this evaporated more so than in the Texas City Y case. So this didn't go on as long. We were fortunate there. But again, this was a long day, right? And a deployment. And then Melissa went back the next day, I believe, to help out. So happens quick. And then I've talked about this a lot recently. So you may have heard some of this, but the ITC tank farm fire was another really big one. Again, started in March 2019. And the big deal with this was the smoke plume. You know, this lasted a while, it escalated, and it was actually happened after another explosion that happened at the ExxonMobil plant that fortunately wasn't as big of a deal. But our initial support to emergency managers was similar to what mini office would do. We ran a high split early on, and then we transitioned a little bit during the event later on, but this was a valuable tool to track the smoke plume, and that went to emergency management. But what's interesting in this case is it attracted a ton of attention because this massive black smoke plume just lurked over the Houston metropolitan area with 6.5 million people. And it wasn't particularly dangerous at the time because it was a loft, but it was ominous. And so the media really wanted support for this. But I'll throw the flip side on this. What if you have something near the surface happening, like what happened in 1976 in the Houston area in Southwest Freeway and 610 Loop, where a tank of 7,500 gallons of anhydrous ammonia turned over? Now you can't use high split, and you've got to be quick, or people might die. And in that case, 7 people died and hundreds were injured. So back to Deer Park, the escalating support. Well, we talked about Sean earlier. We brought Sean into our office pretty early on in this event to help track the smoke. He's also an air resource advisor for wildland fires, in addition to being an IMET. So he has some experience of tracking smoke. So he used the radar, he used these high split runs, and he created the smoke plume and how it might behave, and satisfied the media request. We got a request from our ABC affiliate, Travis Herzog, and he basically said, hey, I know you're doing this high split. I can download high split myself. Can we get this output and show people how this plume is going to behave? And so we basically said yes, but kind of had to figure that out because it's fairly technical information with the high split, and you don't really want raw high split output going out to the public. And then on the right, you see some other things that we worked on. And this was an air quality outlook for the Deer Park fire. We've never really done a public air quality outlook. Of course, we're using TCEQ data, but we're trying to show how the air quality can change during the day. It wasn't just, some of this was due to smoke, but a lot of this was due to ozone. So there was really a lot to explain here and a lot of expertise needed to understand what was going on. So another thing that happened that was rapid was staff training, because after we created this public smoke plume, we've got to keep creating this public smoke plume. And then the need even changes and gets refined. So at first we send them an image. Now we need to send them a KMZ file so they can put this in Google Earth and show where it is relative to Houston. So we did that, and we started showing time steps because the plume changes and it's easier to understand if it's not in just one graphic. And this is just page 1 of many instructions that we rapidly trained our staff with. So Sean did deploy here right after coming in and helping out with the smoke plume product. Then we send him to our partners. And the big advantage here is he's in the room and he really knows what's going on and can answer questions. So here he is at the Harris County Operations Center. And he helped craft some more public products. So this one, when the fire went out, and so this material is no longer being lofted, now we end up getting a benzene threat near the surface. So basically all that fire retardant material and foam that was sprayed on the fire, there's cracks in it. And some of the benzene starts to seep out. And of course, benzene's a carcinogen. And so we had to worry a little bit about how that near surface wind flow might shift the benzene around. So there's some shelters in place in the Deer Park area, and we need to explain to the public what was going on. So he worked on that with Jeff Lidner there that you see in this slide, who's the Harris County meteorologist and also a flood expert, as you might have known from Harvey. So there's Sean building some partnerships, and we appreciated that. Yeah, so a containment wall breached not long after the fire went out, and all that fire retardant material, or at least a lot of it, and whatever else remains, now moving into the waterway and in the ship channel. So now you're in it for the long haul, and your support changes from the air to the water, which is now a different expertise. So we did have some help from the NOAA experts, obviously, and they kind of took over, but we had to still provide them weather support because they're out there in the water, trying to contain this. And this went on well through mid-April. So you can see, it's really important to develop a responders culture. If you're going to promise the support, as we do in the Weather Service with our decision support services, we've got to be ready, either remote or on site. There's a role for both. And then if it is on site, you're going to have to be ready to go quickly and whenever it actually happens. And sometimes, it's not exactly weather that's causing it, so you can be completely surprised. So Sean took this picture. I guess he was driving around and he saw the plume on the weekend there. I think this started on a Saturday, and he knew he probably wasn't going to be long before he called in. So I think he got ready as soon as he saw the plume there off in the distance. So this wasn't hazmat, but it was interesting. It happened about a month before Deer Park. We had the Atlas Air. It's actually a 767 there. This flight crashed in the northern part of Galveston Bay, what we call Trinity Bay, and we real quickly had to support everybody going out for that cleanup and recovery effort. And so again, we're doing spot forecasts, not needing to do high split in this case, but do need to communicate tides and of course any lightning threat and wind shifts and things like that, as people are quickly in the water trying to find people or the black box that they need and just grab all the debris that's out there. So you can see the need to always look for opportunities to train and train different kinds of events. You want to hone your skills and exercises, and again, make them kind of wide varying. So we have a pretty extensive hazmat guide and instructions. We do practice this occasionally going through, and it's very detailed. It tells you which button to click and which step goes next, because we have things like MARPLOT for marine, Cameo Aloha for near surface incidents, and then of course high split is lofted. And now we're starting to make a transition into HPAC, which is more complicated and even more training. So the last kind of topic we're going to talk about is how weather can actually cause the incident and break things. And I'm sure many of you are aware of this with tornadoes, hurricanes, and floods. But in Houston, we've seen major floods often result in a cascading hazmat event. And that definitely happened at Arkema when you're your busiest during the middle of Harvey. They lost refrigeration due to the flood. And then we had a pretty big explosion that grew. And we had to have shelters in place. We had to bring in experts from the outside to help us with some of that plume modeling as well. And then again, not hazmat here, but also caused during a weather event. Just last year, about this time of year, Tropical Storm Imelda, breaking a barge loose in the Houston Ship Channel, and it collides into I-10, and now the bridge is closed, and we have to support getting that bridge back up and running. Just happened, gosh, it's only been about a month, but Hurricane Laura at the Biolab chemical plant near Westlake, a chlorine leak at basically, I think it was a swimming pool product factory, caught fire and exploded. And now we've got another shelter in place and another plume to track. And again, I-10 takes the brunt. Again, I-10 is shut down again. So yeah, I-10's not a road to be on if you don't have to be, right? But no, in all seriousness, this is happening quite frequently in big weather events. And so my last slide, just kind of a shout out to our office who's had a lot of work to do with hazmat and this summer tropical events as well. You can see we're all kind of, a bunch of us were together at shift change during Laura in this picture. Unfortunately, we had no hazardous weather to deal with. I think Brownsville actually dealt with the explosion there in Lake Charles in backup mode. So that's another thing to think about. It might not be your forecast area. It might be a forecast area you're just supporting because of a giant weather event. But again, develop that responders culture and give partners the information they're going to need, when they need it and quickly. And with that, I think I'm done, Nick.
Awesome, great presentation. I think you guys and Slidell kind of duke it out for who has the most hazmat events, but I think you probably have the edge, but who knows what the numbers are. I just had one question, and then we'll go on to break. So do y'all do a lot of tabletop exercises with your partners, or do y'all just have enough real-time events to where y'all just deal with those and then kind of do after action reviews on that?
Yeah, it's a mix, but we do have a lot of tabletop practice exercises. We did it with Galveston County quite a bit last year until COVID. We had a big one going on where we would have different hazmat events happen and there's weather going on. And we've done it with Harris County as well. And we also have the IWTs, integrated warning team meetings, and we can go over our hazmat events there as well. So yeah, it takes a multi-dimensional angle approach to be ready for these things.
That's a good point about the IWTs. Yeah, those are very good avenues to use for broadcast EM, NWS, and stuff like this. Well, thanks, Lance, for filling in for Sean. It was a good presentation to learn about what you guys do there and all the different hazmat incidents you have. So with that, we'll take our first break. So far, so good on the technology-wise. We'll leave this stream up for the 30-minute break, but we'll get started right at 9:45 to get on schedule. So we'll see y'all back in about 30 minutes or so.
Hello. Okay. All right. Can you see the title slide? All right. Very good. Thank you.
All right, everybody, we'll start back in about 3 minutes to go. Todd's ready to go, and we'll get started right at 9:45. We're about to start session 2 of today's conference, Fire, Weather, and Air Quality. We'll start off with Todd Lindley from the Weather Service in Norman, followed with a wildfire talk, followed by a fog talk, and then the theme of the conference was going to be some dust and air quality since we were in Lubbock. So we'll have several talks about different impacts with dust and what that can bring to those areas in West Texas. So we'll go ahead and get started. Todd Lindley is the Science and Operations Officer at NWS Norman, and we'll talk about probabilistic significant wildfire potential outlooks.
Well, good morning, everyone, and thank you. Yes, today I'm going to briefly talk about the history and the process of producing probabilistic significant wildfire potential outlooks as part of the Southern Great Plains Wildfire Outbreak Working Group, and I'd like to acknowledge my co-authors. I'll begin this morning with a quote from renowned fire historian Dr. Stephen Pine. In his 1982 book, Fire in America, stated that fire behavior deals with statistical ensembles. Wildland fire does not merely resemble a climatic or meteorological phenomenon. It results from them and is thus another order removed from simple determinism. That statement fundamentally argues against our legacy deterministic red flag warning program and supports something like what you see on the right, a more probabilistic approach that is more readily useful for resource allocation into areas of higher risk. To provide that kind of service, we first have to acknowledge that wildfires are in fact a type of storm, and that they're not only analogous to severe thunderstorms and tornadoes, but many times here on the plains, they result from the same parent synoptic scale weather systems. Dr. Pine also stated that fires are atmospheric events as much as dust devils or hurricanes, which also organize heat release from the surface. So in 2006, 2007, we began some very rudimentary scientific studies of the synoptic scale weather systems that produce these type of widespread fire events on the plains in a way that was very analogous to early severe storms forecasting studies in the 1950s, in that we produced composited conceptual models of these events during the peak burning period of very widespread dangerous fire events across the area, to see what a snapshot of the atmospheric conditions are at various levels across the atmosphere during these events. And what we found was that even though you have a very well-defined synoptic scale weather pattern that supports them, we did have a surprise event in April of 2009 where a composite pattern set up, and conditions were quite favorable for fires from roughly Amarillo down to Lubbock. But instead, fires congregated along a low-level thermal ridge near the I-35 corridor in central Oklahoma to western North Texas. And not only were the fires along the low-level thermal ridge, but they were especially intense where that low-level thermal ridge was intersected by a mid-level speed max aloft. In an after-action report from the Texas A&M Forest Service, that report stated that there is a combination of fire weather and fuel conditions that combine to produce regional wildland fire outbreaks, and that in fact the legacy of the April 9th outbreak may be that we're better able to narrow or quantify the area of higher risk for significant fire occurrence. And based on that report, a research to operations working group was chartered with the stated goal producing a 3-day advance notice for future extreme fire events. In February of 2011, the working group issued its first probabilistic collaborated outlook for a high-end fire event, which indicated a greater than 60% probability of significant fires across West Texas on February the 25th of 2011. And that evening, Governor Rick Perry stated that it's crucial that we take steps to prepare for and respond to extreme fires. And with that statement, he mobilized the resources that you see listed on the right into the area of highest risk. 48 hours later, nearly 300,000 acres were ablaze across portions of West Texas. So what is the process of producing a probabilistic outlook such as that? And it's fire, unlike really any other meteorological phenomenon, is cumulative and is highly dependent on seasonal variation and how those variations shape the environment months prior to the event, all the way down to the hours immediately preceding an event where the fire effective weather actually is occurring over high-risk fuels. Dr. Pine states that there will be no fire unless weather and fuels are right. And therefore, in this process, the state forestry agencies provide fuel intelligence inputs, and the National Weather Service provides the weather component. So we'll follow this forecast funnel, if you will, through an example prior to the April 12th and 13th, 2018 firestorms. And in that case, months in advance of the event, it was obvious that warm season rains were resulting in a robust response in vegetative growth across portions of the plains, particularly high fuel loadings in the area grasslands. We were entering a developing La Nina, which is highly correlated to drought on the southern plains. So as early as mid-December, we were able to start holding briefings with state forestry and emergency management leadership, indicating that the potential exists for a very active period of fire later in the winter or into the spring. Once we got into several weeks prior to the event, there were strong signals of drying in the 30-day precipitation deficits across mainly the Texas Panhandle and western Oklahoma. And this was lending towards an upward trend in energy release component toward what we would consider generally a crisis type environment. Along with that, we started seeing increases in relatively small fires or initial attack fire activity. But some of those fires were exhibiting some extreme behavior. By the first week in March of 2018, a multi-agency fuels and fire behavior advisory was issued for large portions of the Southern Plains. And by mid-March, Oklahoma Forestry Service and the National Weather Service in Norman jointly held a briefing for our emergency management community to let them know that it looked like problematic fire conditions were right around the corner and to give them some pointers on how to collaborate with our agencies during periods of active fire. Once we get into that 3 to 6 day window prior to the event in April of 2018, the numerical weather guidance began to really narrow in on synoptic scale weather patterns that resembled the composite for a Southern Great Plains wildfire outbreak. As early as April 7th, we're able to indicate that Wednesday through Friday of next week could be interesting with an escalating trend. And each day with successive model runs, confidence was increasing to the point where on April the 10th, we were able to state that extreme conditions were lending toward potential predictable fire episode with a dangerous fire situation on Friday. Once you get into really that 12 to 48 hour window, the numerical weather guidance is able to resolve subsynoptic scale features that are quite fire effective and where they overlay the highest risk fuels. So that on April the 11th, we're able to state that dangerous fire episodes on the Southern Plains Thursday and Friday, with the greatest concern for ignition of significant fire Thursday afternoon in vicinity of the Panhandles in Northwest Oklahoma, which would then be hit by a strong wind shift during peak burning on Friday, which is a very dangerous situation. As indicated on the 12th, dangerous, potentially life-threatening wildfire episode expected to begin today. So the evolution of our probabilistic outlooks from the day 4 and 5 periods through day 1 looked like this, and you can see the resultant verification where fires actually occurred. And in this 2-day period, we had 40 fires that accounted for 425,000 acres. Unfortunately, there were a few fatalities and a number of injuries and more than 50 homes that were lost. So what are the pieces of the probabilistic puzzle? I won't go through all of these parameters, but to say that there are a number of parameters that lend towards quantifying the statistical and climatological relevance of the fuel and weather parameter space that these fires occur that do lend themselves towards producing a probabilistic output. This output allows the Oklahoma Forestry Services to become proactive versus reactive and allows the Texas A&M Forest Service to move metal, men, and money. But there's a considerable amount of workload involved in this process. And if we look back to 2017, for instance, there were a number of interagency training episodes that occurred, a number of joint briefings. And in a 6-week period from mid-February to early April, when 4 Southern Great Plains wildfire outbreaks occurred, more than 1,800 texts were exchanged between subject matter experts, and those resulted in 138 significant fire potential discussions and 52 probabilistic outlooks. So the way this typically works, the workflow is that 2 National Weather Service forecast meteorologists and 4 State Forestry Agency fire analysts are constantly monitoring for signals of synoptic patterns that match these composites. And we're interacting via text and phone calls. That is all offline. And as soon as a candidate weather system is identified that matches the composites and that we feel has the likelihood of producing significant fire on the Southern Plains, a series of probabilities are issued that state the probability of different fire phenomena. We call this a collaborated occurrence probability of wildland fire. And that is opened up to a larger group of around 85 National Weather Service forecasters, but it stays within the science community at the forestry agency levels. The state of Oklahoma may begin to take action on this type of information because they are more of an initial attack agency. Once those probabilities for significant fire or an outbreak exceed about 10 to 30%, then it triggers the issuance of a probabilistic outlook graphic on the front of the group's website, which is more of a trigger for Texas A&M Forest Service because they are more of a mutual aid agency. So how do we measure success? We try to verify these probabilistic outlooks, and over the last several years, dating back to 2011. Generally, we feel like these are quite well calibrated, whereas if we say that there is a moderate or 40 to 60% probability of a significant event or a wildfire outbreak, that generally occurs about 42% of the time. Likewise, if we say there is a greater than 60% probability or a likely category, that happens, that verifies with an outbreak about 67% of the time. But I think what makes the most difference is the impact these have had on the public. We see about 100,000. If we look at the casualties per 100,000 acres in a Plains firestorm, we see that number has decreased with different benchmarks in this work, from about 7.4 back in 2005 to 2010 to about 2 to even down towards 1.3 casualties per 100,000 acres in a Southern Great Plains wildfire outbreak as late as 2014 and 2017. And I would say it is not the outlooks themselves that have resulted in this improvement. It's certainly the core partnerships that have been developed with the state agencies. So in the future, this type of work might inform a more of a phenomenon-based decision support paradigm for fire services, where you have outlooks that are probabilistic in nature, days in advance, spanning down to the time that a fire actually ignites. You have more of a fire scale warning or notification that fire is occurring, until you have prolonged fires that require incident management support with on-site IMED. And a problem that, it's really dependent upon the fire and its impacts on the public, whether your forecast verifies. And I appreciate your attention.
Thanks, Todd. That's a very interesting presentation. I just have one question for you. So, how do you see this expanding outside your area, and can you tell us more about the buy-in from your local partners on it?
Well, this evolved in a very unique environment where Texas A&M Forest Service and Oklahoma Forestry are very independent of the national interagency fire services. So we had a lot of latitude to do science and innovation here. I think there are certainly components of it that can grow upscale and be applicable across the country, but it will take very robust relationships between the fire agencies and the Weather Service to do so.
Sounds good. Thanks for joining us. Very interesting presentation. I like what you guys are doing up there.
Thank you.
Thanks, Todd. All right, as Todd transitions out, we'll bring in Jason Runyon. Jason Runyon is a forecaster at the NWS office in San Antonio, and his presentation is going to be about a super fog event that we had on New Year's back in the night of New Year's Eve 2018 into 2019. So Jason, I think your screen's sharing. It looks good, so feel free to start.
Well, good morning. Can you hear me fine, Nick? Okay. Again, I'm Jason Runyon, a lead forecaster with the National Weather Service office out of Austin, San Antonio. And before I begin, I would like to upfront give credit to our Science and Operations Officer, John Zeitler. He did a considerable amount of work with this presentation. So over the next few minutes, we're going to look back at an interesting event that took place New Year's Eve 2019. As we rang in the new year, we also rang in what we'd consider a new weather impact category for our area of responsibility. We've seen this impact category in other areas of the country before, certainly in the southeast U.S., but not here in south central Texas. So during the minutes and hours just after midnight, we began to see patches of very dense superfog develop. And in one particular location that you'll see here in a minute, it contributed to a multi-vehicle car pileup. Now, if you've ever been to Austin or San Antonio for New Year's Eve, one thing you probably know is the cities know how to party, especially when it comes to fireworks. Culturally, in these two cities, many families like to gather, friends like to gather and shoot off fireworks to ring in the New Year's. And this video here that you see is an aerial look at San Antonio this past New Year's Eve 2020, showing the scope of the fireworks at midnight on New Year's Eve. And you can see if you look closely, it might be hard to see streaming here, but if you look closely, you can see the smoke and haze trapped near the surface on the horizon. And it's smoke like this that assisted with the development of superfog in both Austin and San Antonio New Year's Eve 2019. The term superfog was coined by Optmeyer back in 2002, and it's defined as a mixture of smoke and moisture released from damp, smoldering organic material that mixes with cooler, nearly saturated air. And so visibility is often less than 10 feet in superfog situations. Under light wind conditions, the superfog can meander and settle into lower terrain. These conditions have been seen in various parts of the country, as I mentioned earlier, but are most notable during the cool season in the South and Southeast U.S. in proximity to where prescribed burns and wildfires are taking place. And I should point out that superfog conditions have been the cause of several notable multi-vehicle car pileups in the U.S. Now, while much of the research has been related to superfog in the context of burning of organic material, a lesser frequency of cause is from the smoke particulate produced from the use of fireworks. The superfog generated from fireworks smoke can, as you're going to see here shortly, have the same severity of transportation impacts as that generated from wildfires or even prescribed burns. So Optmeyer, back in 2002, when he coined the term superfog, described the issues with superfog as it related to the wildland-urban interface. And he went on to describe that there are occasions when smoke is entrapped locally, especially in that lower terrain that I mentioned, and can while Optmeyer went on to talk about the importance of modeling smoke from wildfires or prescribed burns to help better predict superfog, I should point out that the modeling of particulate matter from fireworks is nearly impossible. Now, those of you that may like more of an illustration view, here it's shown that carbon and other particulate matter produced from the combustion can actually serve as additional surfaces for water vapor to condense on. And also, in the context of wildfires and prescribed burns, the live and dead fuel moisture vaporization can actually increase the water vapor content, leading to saturation. So as the surface temperature cools to the dew point and the ambient moisture will condense onto these additional cloud condensation nuclei generated from the smoke, forming superfog. And again, it's defined as visibility is less than 10 feet and basically zero visibility. The superfog index, or SFI, seen here was adapted by Gary Optmeyer's work. The SFI is the probability of superfog formation based on different temperatures and two relative humidity scenarios. So as you see here, when smoke is present and RH and wind conditions are right, it's likely that superfog will develop during cooler temperatures. The SFI increases rapidly at air temperatures less than 55 degrees Fahrenheit when RH is 90% and 45 degrees Fahrenheit when RH is at or above 90%. So this brings us to the events that took place in our area back during New Year's Eve of 2019. So let's first kind of take a look at the synoptic setup. Here's the 0Z 500 millibar analysis. And you can see South Central Texas, noted there with the yellow dot, is between a trough over the Great Basin and the subtropical ridge to the east. Looking down lower at 700 millibar, that reveals a similar pattern with a trough to the west and ridge to the east, and also reveals mid-level dry air in place. And at 850 millibars, a trough was seen moving into the Texas Panhandle and Oklahoma, and very dry, weak southwest flow over South Central Texas. 0Z surface analysis reveals the surface front over the Panhandle of Texas and Oklahoma. Clear skies and light to calm winds were in place across South Central Texas, with temperatures at 6 p.m. in the low 50s and dew points in the mid 40s. So as a forecaster, when you walked in that evening, you might be thinking that it was probably going to be a report at midnight, indicating shallow, moist near-surface conditions developing beneath an inversion and dry air aloft, indicating clear skies. And the near-surface winds were forecast to be around 3 knots or less. And so this buff kit sounding was also indicating fog was favored. on the east side of Austin from New Year's Eve of 2019. The top graphs show temperature in red and dew point in blue and relative humidity in green. And the bottom graph shows wind speed and direction that was observed. Circled there, kind of in the purple shading, is the time frame of interest from around 11 p.m. to 3 a.m. from New Year's Eve, Central Standard Time. You can see saturation occurring shortly before midnight at Austin Bergstrom and just after midnight at Austin Executive. And if you look closely, the temperatures ranged from about 37 to 42 degrees Fahrenheit. And if you recall from the SFI slide that I showed earlier, those temperatures with RH above 90% are ideal for superfog formation. And so this time also coincided to the peak of firework activity for New Year's Eve. At the same time, on the bottom graphs, you see the wind speeds became less than 5 miles per hour to even calm. This is a time lapse from our tower camera in New Braunfels, just down the road, from 11:30 p.m. to 12:30 a.m. New Year's Eve. It may be kind of difficult to see this streaming over the internet, but there are fireworks seen on the horizon being launched through this time period, again, from 11:30 to 12:30 a.m. And you can initially make out the smoke being trapped beneath the very shallow inversion. And eventually, in the foreground of the vehicle accident occurred after midnight on State Highway 130, close to the Austin Bergstrom International Airport. Also, if you look closely, the yellow line on the map is the Colorado River. What we suspect happened is smoke particulate produced from the fireworks remained trapped beneath the inversion late that night, and the light winds that developed and cool air drainage allowed it to settle into or near the Colorado River basin late that evening. And so as saturation was reached, we suspect condensation occurred on these additional nuclei producing the superfog. I should point out the patchy nature of the superfog could have also created an even worse scenario, as motorists who were going the posted speed limit of 80 miles per hour on this toll road may have rapidly encountered the near zero visibility with little to no warning. The next video I'm going to show you here is actually taken from a motorist inside a vehicle during the accident.
Get out of the car!
Again, this is on the toll road, an 80 mile per hour toll road with dense superfog. So you can clearly see here, this isn't your typical dense fog advisory night where visibilities are down around a quarter mile. This is visibility less than 10 feet. Altogether, 35 vehicles were involved in this pileup at this spot on the toll road on the east side of Austin. 56 people were injured and 9 were transported to hospitals. So you remember, as I mentioned earlier, when we looked at the analysis, remember that shift that you thought as a forecaster was going to be quiet? Well, now you had a shift with a level 3 mass casualty incident that was occurring in your CWA with an incident command staff spun up by both the Austin and Travis County Emergency Management partners. And just to show you, this just wasn't one isolated spot in our area where we had patchy superfog. We saw this patchy superfog all through the I-35 corridor that night, including in San Antonio. These pictures were actually taken out of San Antonio on Loop 410 on the south side of San Antonio just after midnight, where superfog had developed. Fortunately, in San Antonio, we did not have any accidents attributed directly to the superfog. So how can we better anticipate these events? And how can we, importantly, tailor our messaging to mitigate the risk and the impacts? Gail Hartford of the NWS Raleigh office had some good thoughts on this. Number one, we need to make sure forecasters have good situational awareness of what superfog is and superfog risk is. Questions forecasters should be asking are, number one, are your forecast temp and RH conditions resulting in a high superfog index number that we talked about earlier? Are there light winds occurring? Are there wildfires or prescribed burns in the area today that could produce smoke that could serve as additional cloud condensation nuclei? And could that smoke linger beneath any type of inversion overnight? This is where the next bullet is key, improving communication with forestry and land management agencies. concerning smoke dispersion. Now, in our case, the smoke was, as I mentioned, the cause of fireworks, which makes it nearly impossible with respect to modeling. So extra situational awareness is likely needed in some cities where firework usage is more prevalent during the holidays. In our case, the midnight shift that night was keyed off about the rapid development of the superfog through webcams and also through Twitter. Tailoring the right message is also very important. Standard dense fog advisories aren't going to work aren't alone going to work during a superfog situation. Utilization of graphics, social media, NWS chat, and even DOT message boards are all very important delivery methods during a superfog event. So let's fast forward a year and move on to the New Year's Eve of 2020 that we rang in. Much more situational awareness was present by our forecasters in our area this past New Year's Eve. We saw the fireworks happen again, like in previous years. We saw smoke hovering beneath a developing inversion late that night and into the early morning hours of New Year's Day. Visibility did lower in some spots to a quarter to half mile from the smoke. But the temperature dew point spreads this past New Year's Eve were too great for the development of superfog. So actually this past New Year's Eve, it became not a superfog issue, but more of a widespread air quality issue. And you can see there on the right, the air quality index reached the unhealthy category overnight. Here is the tower cam from our office in New Braunfels. Again, this is from New Year's Eve 2020, from the time frame of 11:30 to 12:30 a.m. Might be kind of hard to see streaming, but no superfog development. But as I mentioned, our forecasters were situationally aware. On the right there, you can see the previous day shift on the 31st had discussed in the area forecast discussion that the setup wasn't ideal for superfog, but smoke could linger near the ground. So the smoke actually was included in our forecast grids, anticipating an air quality impact this past New Year's Eve of 2020. And this was actually also picked up by some media outlets, including both the Texas Public Radio and Capital Weather Game. So again, extra situational awareness is key during these superfog events. One year it might be, a relatively quiet night you're dealing with. The next year, it could be superfog contributing to multi-vehicle car pileups. The next year, it could be air quality issues. You just never know. So with that, I think I'm running kind of late here on time, so I'll pause. Here's my email contact information and John's email contact information if you have any questions.
Thanks, Jason. We had one or two questions. I'll ask the first. Basically, the question was, and you kind of talked about it at the end before, after the question was asked, but have you examined the impact on the air quality and the particulate matter measurements? And I guess my question with that would be, is there do you know if there's any minimum levels of smoke or air quality issues to where the superfog can form?
So part of Octomeyer's work was something called the smoke dispersion matrix. I didn't have time to show it in this presentation, but it's a matrix that kind of goes through some of what that question was alluding to as far as smoke and stability class. And so that's something certainly to look at, is the smoke dispersion matrix. And also, I didn't have time to show it, but there is for the WFOs a superfog tool that's out there on VLab that was developed by Josh Weiss that goes through several different parameters that can serve as a forecaster aid, not necessarily a decision tool, but a forecaster aid for superfog events.
Awesome. Well, thanks, Jason, for that presentation. Working in this office, I was super glad I was off that night. So I didn't envy those who were working then. So next we welcome Dr. Arden Dreyer from Texas Tech University, and we'll get into the dust aspect of this session. And looks like she is beginning to share her screen, so I will hand it off to you.
All right. Can you see the screen? All right. Can you see the full one? Because I cannot see anything. All right. All right. Good morning, everyone. This is great opportunity to tell you about one of my favorite topic, which are dust storms. I'm very happy to be the first one who kick off this topic. And today I'm going to tell you about characteristics of a different type of dust storm as measured by AROS. So if you live in West Texas, you are no stranger to dust storm. Dust storm are a meteorological phenomenon that occur mainly in arid and semi-arid environment. And we have here, and this is really a name that used mainly in the US, a haboob, which is one type of dust storm, mainly from convective storms. A haboob is basically saying dust storm in another language. It's something that brought up back in the Gulf War in '91 from a soldier who were deployed in the Mediterranean. But here we have this definition of this wall of dust, calling it a haboob, and a regular synoptic dust would be a regular dust storm. So here in Lubbock, we have these two types of dust storm. We have convective event. Sometimes they'll form a haboob type, and we also have a synoptic event. And we notice that there's some seasonality in their present, and their impact is very different. And if you want to hear more about it, I'm inviting you to the last talk of this conference that will talk more in depth about this. But when we examine some of these storms, we notice that there are some changes in the particulate matter. So the PM2.5, these are the particles smaller than 2.5 microgram that we have here. And these are the slide that you see here at the bottom are different plots for different days that we had dust storms event. And the black line represent those PM concentration, and you can see that some of them are very high, some of them are very low. But these are hourly measurement. And we know that some of the synoptic event can last for a very long time, several hours, and some of the convective event can be very short. So we wanted to examine what are the differences or similarity between these dust storms. And we need to do that at a short duration of time scale, because if we'll only look at an hour average, we will miss some of the dust storms. So in order to do that, I build AROS. AROS is Aerosol Research Observation Station. It's located at Texas Tech University on the rooftop of Electric Engineering here in Lubbock, Texas. And in this station, we have multiple types of instrumentation. We have instrumentation that measure aerosol total concentration at different sizes. We have instrumentation that tell us the size distribution. So we know how many particles we had at different sizes, starting from 200 nanometer up to more than 35 micron. We also have particulate matter. We have measurement of PM 2.5 and PM 10, particulate up to 2.5 or particulate up to 10 micron. And we have those measurements every minute from those instrumentation that you see here inside the station. We also have a small meteorological station, as you can see on the rooftop. It's a Davis meteorological station, and we also have the additional Texas Mesonet and our local National Weather Service station that we compare our meteorological measurement to. In addition, the white bucket that you see here are gravimetric measurement. These are PM 2.5 and PM 10 measurement that we take on filters. It's 24-hour average. And then we can take the filter to the lab, analyze it under the microscope, and also expose them to cells. So I want to give you an example of 3 different dust storms that we had back in 2012. I should say that the station has been operated since March 2019, and the 3 dust storms happened in 2019 in April and 2 events in June. So the first one I want to show you is the April event. As you can see here at the top, these are the different meteorological conditions. We have in green the wind speed and in black the visibility. And I'm going to go over each one of these dust storms. So the first April 10 event was a synoptic event, and I think we're going to hear about it quite a lot today. There's additional talk about it. And this event was initiated from a front that passed this area, and you can see in this video this cloud of dust that are just coming and passing our area. So you can see this cloud of dust coming in, and it's really correlate with how the wind increased and how the visibility decreased. So this was a synoptic event, and one of the biggest one we had since the station was operational. The second event, or actually the two events of June, were convective event, but they're similar but also different. The first one, we had a convective event in the form of a haboob. And you can see this very sharp decrease in visibility and sharp increase in wind speed. This event was recorded even by the radar that we have here in Lubbock. And this is this light line that you see in front of the clouds. And this is how it looked like. We're going to see this wall of dust, this big haboob passing over our station. And you're going to see in a few more. We didn't have a wall of dust, a haboob that passed really near our station. We had some thunderstorm clouds at about 70 kilometers away from Lubbock. And you can see how the visibility decreased really sharply and the wind increased for a very short duration of time. And this is how it looked like. This is facing south. And you're going to see this dust passing by our station. So what did we found? All right, so here are just PM measurement from our station. So we have on the left the April 10 event, in the middle the June 5th, and June 21st. So the two convective events are shown very narrowing and very large increase. And on the synoptic event, we see a very wide event, very long. It lasted for 12 hours. And we see this increase and decrease in the PM concentration. And this is because we had some changes in the wind direction. Now here in the different color code are just the different PM that we measure, the PM1 in blue, in orange the PM 2.5, and in khaki the PM 10. Now these are 10-minute average, and you can see how high the number go, more than 1,000, and even with the standard deviation of June 5th, for example, more than 2,000. But when you analyze daily average, and this is what we do normally, we calculate the daily average of these events, and we then compare them to what the threshold of the World Health Organization give us, or what's the EPA threshold. So we can see that the April event really passed that threshold. We have PM 2.5 from the World Health Organization as 25 or 35 by EPA, and we definitely passed that threshold during the synoptic event. For the PM 10, we had more than 120 particle per cubic meter, and we did pass the World Health Organization threshold, but we did not pass the EPA. But what's happening on synoptic event? So as you can see, the value, the average of the synoptic event was in some cases much lower than the threshold that we have, but we should not ignore the standard deviation. And you can see this graph, this huge increase. So although the duration of this increase was short, 20-minute or 30-minute, people who were outside during this event were exposed to a lot of particles. So this tells us something about these differences between these types of event, and this raises a lot of questions, whether convective will bring more particles compared to the synoptic, or synoptic are more severe in terms of the duration of the exposure. Here's another comparison when we calculate the total particle concentration, and these are the different colors represent two different instrumentation. And if we just average dose concentration based on size. So at the top panel, we basically took two instrumentation and we try to have a comparison based on similar size range. We see some differences between them. At the bottom, we compare the total concentration, so from 250 nanometer up to 40 micron, and we see that the two convective events had very similar concentration of particles. Unfortunately, this instrument did not work on the April dust storm, so we don't have measurement from that. But yet again, when we compare the total concentration of the daily average, we see very low values. So this is information that could be very good if you're planning to use modeling, if you're doing stuff for equality or cloud physics. But this is not just telling us how much concentration. We should also consider something about the size of the particles, because smaller particle can penetrate deeper into our lungs, and it's very important to know if we could see those kind of particles in dust storms. So the first step was just to have a comparison between these different type of dust storms. So on the left here, you see a plot showing the daily average of these two convective events, where we're just comparing two instrumentation, just to show that the instrumentation actually give us very similar concentration or size distribution of the particle. But when we look only at the time of the highest concentration of dust storm, so this was late afternoon on April 10, or 6 p.m. on June 5th, or 9 p.m. on June 21st, we start to see some differences in the size distribution. So the concentration is on the y-axis and the size of the particle are the x-axis. And you can see that the April 10 had higher concentration of particles, especially at lower size, compared to the other two convective events. And again, this is something that can help us to see some of the differences between these events. So there is an assumption that dust storm only have large particles, and there's no small particles. But I want to point out this plot showing the time in blue right before the dust got to our station, and in brown, the highest concentration we got during this event. And we can see that even in the dust storms event, we have high concentration of small particles. So this is something we should be considered mainly for people with respiratory problem and pre-existing condition. So dust storm can bring small particles. Here I'm just showing the comparison between those dust storm at the orange, brown, and red color compared to 6 clean days. So you can see that even in some of our clean days, and these are average of 6 different clean days, we still get to see high concentration of small particles. Now, other thing that we can do with our station is we can take the sample on filter, as I mentioned, and analyze the particle. And this is just April 10 filter that we analyze, and we identify a lot of known element that represent dust storm. But the interesting part that we found some nice biological particles. As you can see, those rounded shape at the bottom images, very nice biological particle that could have additional impact on our health. Now, unfortunately, due to COVID, our station has been shut down since March 26th. So we no longer had access to our shed. We had no longer access to our rooftop. But what I did was I basically took some of the instrumentation and brought it home to continue doing the measurement. And you can see some of the images here showing the adaptation I had to do in order to conduct the measurement. And ever since the station have been operational in my house, we have so many exciting events. For example, we had a lot of convective events, and this is just a one-day snapshot of different convective event we had. As you see the image show, this was kind of a cloudy day. But as the time progressed, you're going to see some precipitation event here in Lubbock. And in the late afternoon on that day, we had some very large increase of particulate matter, and they were because of different convective event. And you can see the storm with the image of the radar that we downloaded showing where the storm for this afternoon event occurred and how it impacted. But look at the values of PM. They are much smaller compared to the convective event that we had. So there could be some wide variety of differences between convective event, and this is something we're hoping to look at in the future. The last thing I want to show you is just our ability also to measure some of Sahara dust that reached Lubbock, Texas back in June. And stay tuned to hear more information about it as we're analyzing the data now. And I want to thank the team, my team, and the student who were responsible for most of the data that you saw. Thank you so much for the attention. And if there's time, I'll be happy to grab some questions.
We're about a minute late, but I'll ask one quick question. I noticed in the April 10th that the values for the synoptic event was lower than the convective event. Is that typical? The synoptic events are more prolonged with less of a peak than the convective events?
Just based on this one event that we were able to capture, it seems like it. be a pattern that maybe the synoptic will have less compared to the convective. So we don't know if it's the intensity in terms of concentration or the duration that makes the impact.
Perfect. Well, thank you so much. That was very interesting. I learned a lot from that.
Thank you.
Thanks for joining us. Next, we're going to transition to Dr. Gill from the University of Texas at El Paso, keeping our dust session going. Dr. Gill, feel free to share your screen and we'll get you started.
Okay, good morning. Let's get this going here. Can you see the screen? Okay, good morning. My name is Tom Gill. I'm a professor at the University of Texas in El Paso, and we will continue the dust theme, and I will present a characterization of blowing dust and sand events here in El Paso, Texas, where we're in the Mountain Time Zone. We're an hour earlier than all the rest of you there in Texas. So this presentation will give a brief overview of our understanding of the meteorology, the sources, the climatology, some characteristics, and some impacts of dust and sand related weather in El Paso. And first, I'd like to thank the many people who have worked with us over the years. This is a synthesis of more than 15 years worth of work with many collaborators, students, professionals, other faculty, and I'd like to thank them all. So El Paso is known as the Sun City, and typically, especially during the cold season, the view from the Franklin Mountains overlooking the city like this is beautiful, clear blue sky overlooking the city of El Paso and Juarez, Mexico in the distance. But especially in the spring, by the afternoon, when the wind comes up, it can suddenly be transformed to this, blowing dust and sand. This is unfortunately the most, I would say, the most typical hazardous and impact weather event that we experience in El Paso and the surrounding Chihuahuan Desert. As Karine led in to this presentation, when you think about dust storms, most of the public thinks of these gigantic walls of dust, these haboobs that are driven by thunderstorm outflow. While they're dramatic and picturesque, they are not the most common type of dust event in El Paso. And interestingly, from the previous presentation, again, they're also present in other parts of West Texas, such as Lubbock, but not dominant in West Texas as they are, for example, in Arizona, where they're the most common dust event. In El Paso, though, these convective dust events are the most common type of dust storm during the warm season, especially right at the very start of our rainy season, which we get from the North American monsoon. Especially in June and July is when we get these events. However, the predominant type of dust storm, dust event in El Paso, as it is in Lubbock, you will see in this GOES satellite loop as well, are the synoptic scale events. In El Paso, they're driven primarily by passing Pacific cold fronts and troughs from the west, as well as gradient winds associated with strengthening Lee cyclones to the north and northeast. The next presentation by Laren Reynolds of the National Weather Service El Paso will give more detail of a classic synoptic scale dust event in the El Paso zone. You will also notice, you can see here on this GOES image, that many of the dust sources blowing into El Paso are actually coming from across the border in Mexico. Especially after the advent of the NASA MODIS sensor on satellite that really revolutionized our ability to detect dust events by remote sensing, we've been able to pinpoint hundreds of individual source locations associated with these dust events affecting El Paso. And one of the interesting things that we have discovered is by correlating satellite imagery of dust events and their sources with land cover data, it became very clear that a disproportionate number of dust sources are associated with a specific landform. These are playas, the usually dry beds of ice age lakes in the desert. Such as this. This is a very large playa in Mexico, south of El Paso. In the northern Chihuahuan Desert surrounding the El Paso metropolitan areas, playas like this cover only about 4% of the land surface. But by one of our studies using GIS to tie everything together, playas were the initiation point of almost half of all of the dust plumes visible on NASA MODIS imagery. And you can see why. When the water dries up after the rainy season, you get this very, very flat bed of loose sediment that is windswept, very little or no vegetation to break the wind. So perfect opportunity to pick up lots of sediment from a loose, flat surface. Now let's go into some of the climatology of our events. They're primarily from the Southwest. The long-term climatology is consistent. More than half of the blowing dust and sand events in El Paso come from the Southwest, with a smaller number from the Northwest. Occasionally, backdoor cold fronts blow in dust from the Northeast, and the least frequent wind direction associated with blowing dust and sand is the Southeast. At El Paso, the National Weather Service has been tracking these events since 1932. Over the long term, El Paso has averaged 15 days per year with dust. The classification is a little difficult. Dust storms, by official definition, require visibility of less than a kilometer, and they're rare. Blowing dust has been assumed to be the more appropriate term. However, the true number of dust events, especially when you go back in the records, is a little fuzzy because some days when dust was clearly going on are coded as haze. That's really a problem internationally with studies of dust storms everywhere. And you will see that the greatest number of dust storms, 49 per year, happened during the Dust Bowl in the 1930s and the so-called Filthy 50s in 1954. In terms of annual climatology, there is a very strong peak in the spring, especially around mid-April, where events peak in April. The duration in terms of total number of hours, because the synoptic events last longer, is much stronger in March and April. And then there's a drop-off in frequency. And during our rainy season, the monsoon, from late June through September, dust events are at their least frequent, and they're primarily the convective events. There's a very strong relationship of dust in El Paso to drought, as well as ENSO. Dust events are strongly favored during drought conditions. This is association with PDSI of every dust event going back to 1932. Wet on the right side, dry on the left, and you see a very strong association with PDSI negative or drought conditions. There's 236% greater number of hours of dust during La Nina conditions versus El Nino in El Paso. And that's to be expected because in our region, La Nina is strongly associated with this drought. So how much dust do we get? Measuring the amount of dust falling into dry deposition traps is a standard method of measuring dust fall. The average deposition rate measured over a 5-year period in El Paso was about 111 grams per square meter per year. That's ranged up to about 160 during the very strong drought of 2012. So that's between about 1/2 and 3/4 of a ton of dust and sand per acre falling out of the sky in El Paso. That puts El Paso in, honestly, is probably the dustiest metropolitan area in the Western Hemisphere. This is a graph of dust deposition rates globally, assembled by Lawrence and Neff. And if you were to superimpose El Paso on there, it would be this red line up near the top. Fortunately, even though they're definitely amongst the highest in the US and the Western Hemisphere. One of the surprising things we found out when we measured the characteristics of this dust, what we thought was dust falling out in El Paso, is that really about 3/4 of it, these are graphs for annual values averaged over the course of a year, 3/4 of the fallout was actually sand, not dust, although we do get dust going down to very, very fine particle sizes. In terms of the predominant stuff that's blowing around, I would say that these events in El Paso can properly be called sandstorms, not dust storms. The composition of, I'll just mention very briefly, it's the common minerals from local desert soils, quartz, feldspars, caliche, and a bit of gypsum blown from the white sands. Although occasionally we see unusual biological materials in our dust as well, such as the eggs or resting stages of little critters such as tardigrades and rotifers and aquatic tiny organisms blown out of those playas looking for a new home by traveling on the wind. In terms of impacts, dust and sand from El Paso can be blown extremely long distances, all the way to the Great Lakes, the Northeast, and even Canada. I'll defer to the next talk by Laren Reynolds, who will give a great case study of that. Observed at El Paso Airport, the PM10 concentration at UTEP, at the TCEQ air sampler, averaged 172 microns per cubic meter, while it was down to only 25 microns per cubic meter during hours when there was no dust. So a 7-fold increase in PM10. Likewise, PM2.5 average over, this is over 15 years or more, went from about 7 micrograms per cubic meter during non-dusty conditions to over 26 during hours where dust was being reported. So about a 4-fold increase of the very, very fine particulate concentration during dusty hours. And that has health impacts. There have been a number of studies we've participated in looking specifically at the environmental health impacts of dust. And we see a clear relationship between dust events and things such as asthma, which peaks on the day of a dust and sandstorm. Bronchitis peaks the day after the dust or sand event happened. Interestingly, women and girls appear to be more susceptible to the respiratory health impacts of dust and sand in El Paso. And children are more susceptible, especially to bronchitis after a dust storm, than the general public. Finally, a growing concern in our region and throughout the Southwest is valley fever, a potentially severe, sometimes even fatal fungal disease associated with soil and liberated into the air and breathed by people during dust conditions. Valley fever incidence is clearly increasing in the Southwest alongside dust activity, and it is an area of research many of my colleagues and I are now starting to get into. So with that, I'd like to thank you for your attention today. Here's information on how you can contact me. I'd like to thank the sponsors of our research over the years, especially the NOAA Center for Atmospheric Sciences and NASA through their Health and Air Quality Science program. Thank you very much. If there's time for questions, I'd be glad to take.
Thanks, Dr. Gill. We had a couple comments. One was that you already answered their question about which was dustier, El Paso or Lubbock. And then we had one confirmation for you that said after cleaning out their gutters, they can verify that there's a lot of sand in their gutters.
Yeah, sometimes it even comes through the window in El Paso and Lubbock. And in fact, I think I need to talk to my colleague, Dr. Ardendreyer from Texas Tech, about doing a formal intercomparison between El Paso and Lubbock dust conditions. We'll find who is the dustiest of them all.
There you go. Well, we thank you for joining us this year, and thank you for your presentation. We'll go ahead and transition to that next talk that Dr. Gill is referencing with Laren Reynolds from the NWS in El Paso. So go ahead and share your screen, and we'll get you up and going.
All right. All right. Perfect. Well, my name's Laren Reynolds, and as you noted, I'm a meteorologist for the National Weather Service in El Paso, and I'm going to share with you a really interesting case where a low pressure system brought damaging winds through the southern plains, picking up dust originating in northern Mexico and West Texas in the El Paso area, and transported it as far as the Great Lakes region in southern Canada. Now, the dust plume was dense enough that it could be seen on satellite imagery from West Texas all the way through the upper Midwest. And while long-range transport of dust is not uncommon, as Dr. Tom Gill at the University of Texas, El Paso just talked to us about, and he's shown in his extensive research, this case does provide some fantastic satellite and radar visuals, which we'll go through. And this event also helps shape how we message dust events to partners, which I'll share with you at the end. So that's what we'll go through. We'll talk through this case study of April 10th of last year because it's a fascinating one. And then we'll get into how it has shaped how we message to partners. All right, so what I want to go through first is just a little bit of the meteorological setup that led to this event. And the reason why I want to do that is because this event resembles a classic wind or dust event for our region. And what we're looking at is 500 millibar wind speed and height. This is the HREF model that SPC creates, and the temporal scale is hourly. And we're going to go through and watch this trough as it develops. You'll see the wind speed shown by colors. The yellows and oranges denote 70 to 90 knot winds, and the cooler colors are much weaker winds. So as we play this, we're going to see this trough. It's going to move east. It's going to dip below the Four Corners area, send a 100 knot jet streak through southern New Mexico as it ejects around the trough, and it's going to move into the upper Midwest where it continues to strengthen. So again, it's the setup and the upper levels is just a classic one for dust events for our area. Let's go through now and take a look at the surface pressure map. And of course, our eyes are drawn to the low in eastern Colorado. This low underwent Lee cyclogenesis, where it deepened quickly, created a strong pressure gradient against or around southwest New Mexico, which greatly increased our winds. And as we see the evolution of this and go forward in time, we're going to stop it here as it goes into southwest Kansas because you're going to see, and I know it's really hard to see, but there's a dry line here. And where this dry line and this cold front meet up, it's going to provide a source of lift that will be important for future slides. All right, we'll take a quick look at the visible satellite and the evolution of the dust plume on visible. Now, Dr. Gill has just shown us the numerous dust sources in the El Paso region. I am just going to highlight a few because you're going to see streamers from this, from these dust sources from when the wind picks up the dust, and you're going to see the dust plume evolve from these sources. And then I went ahead and plotted some wind gusts, peak wind gusts hourly, so we can see, the evolution of the dust plume. So again, many dust sources. Around 1 p.m., we see some gusts in the 40s and 50s. 2 p.m., so we even start seeing some 60s in there. And then again, you see that dust plume thicken up. And by 3 p.m., we even see some 70-mile-per-hour winds in there. So it's a cool way to see it visually on visual satellites. Another way to see it is by taking a look at the dust RGB from GOES-16 satellite. Now, the hot pink picks up the dust plume beautifully. You'll see it spread over southern New Mexico and West Texas. It continues into North Texas and Amarillo's area, and then eventually into southwest Kansas. So again, just another way to see this beautifully. All right, so we had all the great ingredients come together to create this massive dust plume. We had a synoptic system, we had very strong winds, we had no recent rains. In fact, it had been about 30 days since we had last seen rain at the El Paso International Airport, and our dust sources were primed. So whether it be from cattle or other farming that helped disrupt the topsoil or even soil erosion, the disturbed soil was sitting there just waiting for the wind to pick it up. So that's all really interesting, but I was curious about how the dust ended up in the Great Lakes in Canada. So let's just dive a little bit deeper in this. This video and a few others you're going to see was created by Scott Bachmeyer, who procures the satellite blog for the Cooperative Institute for Meteorological Satellite Studies. And what he did was use the GOES split window images, which shows the density of the dust plume a little better. You'll see it in blue and yellow colors. And he also plotted surface visibility. Now, most of you know this, but visibility is a distance at which an object or light can be clearly seen. So as those numbers decrease, that roughly is the number of miles that you can see in front of you at that time. So let's watch this as the dust plume evolves. You'll see almost immediately in the El Paso area, forecast area, you see Deming is already down below 1 mile visibility. Cruz is at 7. Parts of El Paso is at 4. But all along the path of this dust plume, you're going to see visibility decrease. Already through Lubbock and El Morillo's area, visibility is decreasing. But I want to show you and point out the leading edge of this dust plume. As it gets into southwest Kansas, we see Dodge City drop down to 8 mile visibility, Garden City down to 5. And as you go northeast of this, you see that there is 10 mile visibility. There's no visible visibility issues at the surface. So that tells me the dust plume is in the atmosphere at this point. And the surface obs I looked at as we move northeast also verifies this. So here's another way to look at this. It's a split window again with frontal analysis plotted. Now, you know, the frontal analysis is plotted hourly, so it's going to lag just a little bit behind the satellite imagery, which is plotted more often. And so the blowing dust, again, is going to be in the yellow and blue plumes. So the dust is initially going to develop behind the cold front, and it's going to continue to move into southern New Mexico and Lubbock and Amarillo's area. I'm going to stop it here when it gets to southwest Kansas, because the plume interacts with the cold front and dry line. So what happens here is that it gets lofted over that cold air mass or the cold dome of air, but stays in the trajectory of the system. And this helps the dust to stay lofted, traveling all the way to Canada instead of eventually dropping. So that's neat, but I was curious if we can see this on radar. So I took a look at radar imagery all along the path of the dust storm. For this presentation, I'm going to focus on the merger of the cold front and dry line in southwest Kansas, because I don't have time to show you all of it. So the cold front and dry line shows up on radar as long, thin lines of reflectivity because of converging winds at the boundary causes insects and dust and other windborne objects to collect on visible radar, become visible on radar. And I wanted to see if we see the dust or other particles get lofted into the atmosphere. So I took a look in this red box, that area, which is the convergence zone. And so then I took a volumetric scan in GR Analyst, stop it, and then edited down the volume alpha to look at only the negative decibel isosurfaces. This one's negative 3.5 dBz. And since radar power or decibel is logarithmic, negative values should allow you to visualize smaller particles easier. Now, clearly all of this is not going to be dust. There's maybe some feedback and some insects and other particles in there. But you can see the trajectory of the particles as they move through pretty well. So right now, I want to point out that there is height plotted in the background. All of this stuff here is less than about 5,000 feet, so things here are still surface-based-ish. Let me back up. And so as we go forward, you're going to see the cold front come in from the left, the dry line come in from the right, and you're going to see these particles get lofted into the atmosphere, which is pretty cool. We'll watch it one more time. Again, things start out surface-based, but as that cold front comes in, you can already see some lift there and the dry line and those two meet, you see things getting lofted upwards of 25,000 feet or so at this particular point. So here is another look at this. This is the split window satellite view of this system. The dust is going to appear in the yellow, and we'll stop it here. And this is late in the day on April 10th, so that the dust is already over Southwest Kansas, is getting ready to enter into Nebraska and Iowa, over into Omaha's area. I did check all along this route, surface visibility. There's nothing obstructed by dust at the surface. So therefore, at this point, and everything northeast of this, the dust plumes lofted into the air. So we can watch the dust plume in yellow as it moves with this low, goes into the upper Great Lakes, and this is where it eventually becomes entrained in the circulation, where it fell with precipitation, causing dirty snow in parts of Minnesota. Again, we can still see the dust. This is the next day still as it travels with this low. So just an incredible system altogether. And you can still see the dust flowing. It's beautiful. So I didn't have time to get into the impacts of this event because it did cause numerous accidents and brownout conditions across New Mexico and Texas roadways. But this event also made us take a look at how we message dust events and how we attack it. So we do this in several parts. Again, this event was a catalyst for this. So first, we wanted to become more proactive on issuing polygon dust storm advisories and warnings, even when storms did not appear to be a severe threat. And the logic on that was based on local research and collaboration with university partners. We found that a combination of high downdraft CAPE and large dew point spreads produce dust, even from small cells, especially over favored areas. And Dr. Gill showed some of those playas that tend to be kind of favored areas for us that easily picks up dust. So next thing we did was we had face-to-face meetings with key partners responsible for public safety during dust events, including the Department of Transportation and state police, where we explained the reasoning behind the increased dust storm issuances. Now, their problem was that they couldn't necessarily react fast enough after a warning was issued. So we became proactive in making calls directly to state police and Department of Transportation from the operations floor to identify potential dust situations so they would be ready to respond. And this became a huge win-win for all parties involved because of the heads up they received and because many of them were on site. Many times they were able to spot dust storm initiation even ahead of surface and remote sensing indicators. So this helped us increase our lead times with these events. So awesome partnership. We also have a GIS guru in our office. Her name's Eleanor Duvetter, and she spearheaded the development of ArcGIS dashboards for partners, which provide partners a new way to visualize dust events and monitor conditions for their own use. And I realize a static image does no justice in showing off these GIS dashboards, but these dashboards are very dynamic and they've been really received well by partners, but it does help that we involve them in the development of the product, giving them a sense of ownership in what they use during dust storms. So in the end, it continues to be about building strong relationships, even today with all the tools in hand. A nice phone call to partners, it still carries the most weight. So with that, I'm going to end this. Here is my email if you have any questions. And if you do want to see the GIS dashboards, and they're really neat, feel free to email me and I will make sure Eleanor gets that stuff to you.
Thanks for that presentation. No questions, but we had one comment that I agreed with. That simulation using the negative DBZ 3D on GR Analyst was really cool to visualize that in real time. So I think a lot of people enjoyed seeing that. And so thank you for your presentation, and we'll transition to the next one as a talk from another talk on dust. And this was kind of mentioned in one presentation already, but this presentation will deal with the impact of dust storm events on ER visits. So it should be interesting. Thank you.
Okay, can you hear me now? Okay. So let me go over again. Good morning, everyone. I'm Xueping Zhang from Texas Tech University Department of Geoscience. The subject of my presentation today is the impact of the dust storm events on the ER visits in West Texas. As we know, dust storms are very common in West Texas. During the spring, during the dust storm, the PM matter the particle matter will increase. In many cases, PM value exceeds health recommendation of the WHO and the EPA during the dust storm day. There are also some cases that the daily average value will mask the fluctuation of the dust concentration, such as on the October 17th, 2011. Here's the video showing the how survived the dust storm was on that day, and you can see on this plot the PM value will increase in several hours during the dust storm, but the daily average PM on this day was lower than regulation. So as we in this environment, how will the dust particle affect on our health? Please let me introduce about the particle matters first. Particle matter is the blend of the solid and liquid particles suspended in the air. The particles are classified into three classes: coarse, fine, and superfine. Coarse particle has a diameter of 2.5 to 10 micrometers. To provide a conceptual comparison, the diameter of the human hair is generally 15 to 17 micrometers. Cores are hefty and they are less able to suspend in the air. Common cores include dust and pollen. Coarse particle effect on the respiratory conditions such as asthma, COPD, and airway infections. PM2.5 describes the fine particle with a diameter of 2.5 microns or less. Since the particles of PM2.5 are small, they are easier to stay in the suspension. In the nature progress such as dust storm, dust storm will cause a large amount of PM2.5 accumulating in the air. Exposure to the PM2.5 can cause lasting respiratory madness, for example, coronary illness. Because particle matter is everywhere, it turns out that surrounding particle matter is more effective to influence on human health than alcohol or diabetes. And there is a recent paper published in June on the GeoHealth find that an increase on ICU visits on the dust storm days. In their work, they shown that the ICU admission will increase by 48% on the dust storm days, and the respiratory ICU admission will increase 108.4% at the dust days. And their work is focused on the dust storm were reported through the western United States, and Lubbock is also in their test range. Therefore, we have an assumption that the occurrence of the dust storms will affect the visit counts of the emergency room in Lubbock. Furthermore, how will this influence be manifested? So in the previous work of our project, we observed the impact of the dust storm on ER visits from 2011 to 2018. We find 18 clean days which have the PM2.5 maximum value on each day is less than 40 micrograms. And we also find 17 dust storm days which have the PM2.5 maximum value on the dust day is greater than 15 micrograms. And we set the clean days and the dust storm days as the day 0. And when we look on the mean ER visits on the function of time, as you can see, on the clean days, we cannot see any pattern, but on the dust days, you can see some increase on the day 2, day 4, and also a significant increase on day 9. But as you can see, when we add the standard deviation have a large range, maybe because this is the general ER visit count, which didn't classify specifically. Some visitor might have a fever or superficial injury. So we choose to take the data of the ER visits that's only due to the respiratory cause. We analyze Lubbock's local emergency room data from January 2011 to December 2019. We divide the age of the patient into 3 categories: under 18, 80 to 65, over 65 years old. And the gender, we divide into male and female. We average the data by days, and we find that there's a cycle that in winter will have a higher ER visits than other months, which is reasonable because people will get sick more easily in the winter. And we can see a higher increase over the winter compared to other seasons. But when we compare the daily PM2.5 average value with the total ER visit count, we cannot find anything. We also compare the PM2.5 daily maximum value, and we still cannot find anything. So for the further analysis, we took all the 245 dust storm days in these 9 years, and we took all of them PM2.5 data. We fixed the analyzed day range from the 3 days before the dust storm and the 10 days later. And here's the plot. You can see the PM daily average and the daily maximum distribution did increase on the dust storm day. And when we analyzed the ER visits on the dust storm day periods, it did show some fluctuation. But when we add the standard deviation on this plot, we cannot see any statistically difference between these days. And these two are taking the same range of data. So let me go into some more detail about what we find after collaborating the data. We try to divide the visitor by age, and you can see due to the age group, there are some different trend in the number of visits after the dust storm day. And we also divide the visitor by gender, and we can see there are more female patients than the male patient in general, but the fluctuation are not affected by the dust days. We also sort by take out the PM2.5 daily maximum greater than 15, which narrowed down our range to only 39 days. We can still see the peak of the PM values and the visit count on the dust days, but again, when we add the standard deviation, it cannot tell us anything. For further narrow the scope, we divide the course of the dust day into synoptic and convective, and only focus on the day visibility is lower than 1 mile. And you can see the overall value of the synoptic day is higher than the convective days. And if you want to hear more about how we divide the dust storm based on the convective and synoptic, you can hear the last talk of the conference, and one of our group members will talk about this. In conclusion, the ER visit during the dust storm day in Lubbock did fluctuate, and there's no distinct impact on the dust storm or on ER visits in general, but also as a function of age. Maybe because we didn't classification is not specific enough. So for the next step, maybe we will focus on some typically respiratory causes such as asthma or COPD. And thank you for your attention.
Thank you for that presentation. I don't think any questions came over in the chat, but I will say it was very interesting for me as one of my children has asthma. So it's very interesting to see how that dust correlates with ER visits and things like that for folks who have breathing issues. So appreciate your presentation, and we'll begin transitioning to the next one. Get them in here. Okay, hi. So our next presentation is another presentation from Texas Tech University. Your first name is Ziania, is that right? Ramirez Diaz, and this presentation will deal with more health side of it, with the impacts of mineral dust particles on lung cells. So we'll go ahead and turn it over to you.
Thank you. Good morning, everyone. My name is Tianya Ramirez, and I'm a master's student in Texas Tech University, working in the Department of Geoscience in the Atmospheric Science Group. And today I'm going to talk to you about the health implications of dust storm particles in our lung cells. Okay. As we all know, dust storms are a meteorological phenomenon that represent the increase in the concentration of particles and their transportation by really strong currents. Just to have an idea of how large these events can be, that small spot is a helicopter. Okay, but what happens if we breathe these particles? Well, so larger particles, smaller than 10 micrometers, often called PM10, can irritate our nose and eyes, but for people with pre-existing conditions such as asthma and COPD, these particles aggravate their respiratory condition. However, for the smaller particles, it's more dangerous because they can penetrate deeper into our lungs and reach the alveoli and even the bloodstream, and from there reach the brain and heart. Additionally, these particles can carry some anthropogenic pollutants and biological material and put that into our lungs. So there are several ways how we can address this problem. The first type of studies are called epidemiological studies, and they are a statistical analysis of ER visits and medical appointments. In vivo studies are taking place in a laboratory, and they expose live animals such as mouse and rats to this kind of particles. In vitro studies look at cells, millions of cells in a laboratory in a controlled environment to evaluate what happened with the cells. However, sometimes these studies work with millions of cells. So what happens if we expose these cells to 48 hours of dust, and after we count how many cells died? Well, we cannot know if cells died immediately after we add the dust or it took them 48 hours. We cannot see what happened with the cells that remain alive. Are they stressed? Are cells engulfing the particles? All that we cannot see with most of the in vitro studies, and that is the reason why my study goes one step forward to increase the resolution and track cells individually. This method is called the single cell analysis, and here is how it looks like. So we add the dust to the cells, and we can see track each one of the cells individually and see if they died and how many time they take to react to the dust. In order to do that, we use a special microscope that is not only able to take live images, but also maintains the conditions similar to our lungs, which are 37 degrees and 5% of CO2. So I'm working with two types of cells. When a particle enters into our lungs, the particle can find epithelial cells, which make the walls of our lungs, and also it can find macrophages. Macrophages are specialized cells which job is to look for pollutants and dead cells and engulfing in order to take to clean the lungs. So I'm working with both types of cells, human epithelial A549 cells and mouse macrophages Rho 264.7. As you can see, both of them look different. However, they maintain similar characteristics like the presence of a cytoplasm and a nuclei. I exposed them to montmorillonite, which is a clay mineral very common in several dust storms around the world. And we take pictures every 15 minutes during 48 hours to create these live image videos. We expose them to different concentrations, and we track 300 cells per concentration. Well, this is an image that shows how the plate looks like when we add more and more particles. So we see that when the concentration increases, we cannot see the cells anymore. For that reason, each one of the cells has a nuclei marker, a fluorescent nuclei marker that allows us to see the cells. Even if we add the dust, we can continue to look at the nuclei and see if the cells are alive. So with this technique, we can look at cells that are alive, round, white. That means that they are healthy. And in a moment, this cell is going to divide. So we see that the cell is good. However, in the next video, we see, oh, the cell explode, release some of the material. They change in color, in shape. So we know the cell died. And also, we can observe how cells look for uptaking the particles and engulfing them. So this is a video that shows that. First, the macrophages died more as we increase in the concentration of particles, and which differs with the results of the co-author of this conference, Dr. Karin Argent-Dreyer, who worked with epithelial cells. As we can see, macrophages increase the percentage of dead cells with the concentration, but with the epithelial cells, we see that they increase up to 100 micrograms per milliliter. After that, the percentage of dead cells decrease and then remains constant, which tells us that probably these cells entered into an arrest. They stopped dividing in order to avoid dying. We can see what happened with cells that remain alive during the 48 hours, and we see that they decrease the amount of divisions, and this is consistent with both cell lines. They divide less, which means they are stressed. Now, what happens if we combine both cell lines in the same plate? Well, we can do that because each one of the cells has each one of the cell lines contain a different nuclei marker, so we can differentiate between them. And I'm going to break down this graph for you. So with no dust, what we see is that when they are combined, both cell lines die less than when they are separated. But when we add the dust, we see that they have different behaviors. A549 died more under the same concentration of dust, and raw cells died less. So they have a different behavior. And which this tells us is that different cell lines have different behaviors, not only separated, but when they are combined. And also that these techniques allow us to improve the resolution in our understanding of what is the interaction between the cells and the dust. They help us to evaluate cell death and division, and also the exact time of death, the exact time of division, and we can see if the cells are uptaking the particles. I'm going to talk a little bit about my current work. And actually, I'm performing experiments with epithelial cells, but now with 6 different clay minerals. And now we're going to evaluate the mineralogy. Is the mineralogy affecting if cells die more or less? Which kind of elements can make the cells die more. And also, we're going to evaluate it in 2 different size distributions. With this, we can also evaluate the impact of the size of the particles. And we have some evidence that mineralogy can affect the cell viability, and that is what we want to see, but now with this resolution at the single cell level. With that, I'll be glad to take questions from you.
Thank you. Thank you for that presentation. We had one question come in, and the question is, since COVID has a large respiratory impact, is it of greater risk for people living in dust storm areas, or are the people somewhat acclimated being in a dust area? Is there any correlation between COVID and dust?
Well, as I made a study, there has not been a study that evaluates people that has COVID and is in dust storm area where dust storms are very common. However, we have aggravates the acute consequences when it's really fast. These people go to the ER emergency room because they can feel the effects of they cannot breathe or something like that just in the first days after a dust storm. And it's different from people who is healthy because those effects can be seen in a chronic time lapse. So yeah, we don't have exact evidence of COVID correlated with dust storms, but we know that any respiratory pre-existing condition can be aggravated by the breathing of these particles.
Sounds interesting. Thank you. Thank you so much for that presentation. It looks like our last presenter, Theodore Sandu, has joined us before lunch. So we'll go ahead and get started with that one a few minutes early. This will wrap up our talks about dust for today. And he's going to look at the analysis of dust storms in Maricopa and Pima, did I pronounce those counties right, in 2005 to 2018. So Theodore, I'll go ahead and give it to you to present.
Thank you for the introduction. Hello everyone, my name is Theodore Sandu, and I am an undergraduate student at Texas Tech University, currently conducting research in the Department of Geosciences, and more specifically, the Atmospheric Science Group. Today, I will be presenting my project for the past year, which is the analysis of dust storms in Maricopa County from the years 2005 through 2018. Maricopa County, if you're not familiar, is located in the state of Arizona. It is in Phoenix in 2018. And these haboobs receive widespread media coverage. And so while this county is certainly not in a pertinent impacts that dust storms can have on our daily lives. So 3 things in particular that I've highlighted here include transportation, agriculture, and health. Dust storms can obviously have a major impact on transportation, as both in the ground and on the air. In particular, you can see the image at the bottom left here is that of Phoenix Sky Harbor, the international airport in the city of Phoenix, and you can see on the left-hand side a haboob rolling through, causing major air traffic control delays and the like. In addition, dust storms can have a major impact on agriculture as well. Dust storms are often correlated with droughts, so they can have sort of like a 2-pronged effect on the agriculture industry, as you can see by this crop field here that has been destroyed by dust. And finally, dust storms can have a major impact on human health. And as Dr. Gill touched on earlier in his presentation, the disease valley fever is associated with dust storms. Valley fever is a fungal disease caused by coccidiomycosis spores, as you can see stained up here with light microscopy. And these coccidiomycosis spores, they live within the first couple of inches of kick up the coccidiomycosis spores living within the first couple of inches of topsoil and aerosolize them. And as a result, people who are outside when the dust storm blows through will breathe in these spores, and it can cause significant effects, as you can see here in the bottom middle picture of a CXR or chest X-ray of a patient with valley fever. This patient has pleural inflammation here, as you can see in the white of the lung space. And so while valley fever doesn't have a cure at the moment, it certainly is a serious disease to be reckoned with. and understand dust storms as well. So dust storm causes. Dust storm causes, as people have touched on earlier, can primarily be caused by two different sort of weather phenomenon, convective or synoptic classifications. Convective dust storms are generally caused by convective currents in the atmosphere. So in the state of Arizona, it gets very hot, and during the afternoon heat is when typically you will see these convectively generated dust storms producing the downburst in red right there. And that gust front, or that outflow from the downburst will sort of kick up the dust, and the outflow will take the dust along. And so you'll see that like line, as you can see in the bottom right there, of that advancing wall of dust that people like to photograph. And that is typically called a haboob, as you can see in the pictographics right there. On the other hand, synoptic dust storms are generally caused by upper low pressure systems or fronts that move through the area. Key terms include the lows that move, troughs, as well as fronts and jets. The GIF at the bottom here shows a dust storm that was generated by a front moving through the city of Phoenix. And these key terms I'll touch on in a bit are from the AFD, or Area Forecast Discussion Reports, that I used to classify the dust storms. Here is a map of Maricopa County on the left, outlined in blue. As I said earlier, it encompasses the city of Phoenix and the greater Phoenix area. And on the right is a map of the NWS and PM10 and PM2.5 stations that I used in my statistical analyses of the dust storm data. As you can see, the majority of the stations are clustered within the city of Phoenix, with the exception of one down by Gila Bend and another up in the northeast corner by Tonka National Forest. The methodology that I used to classify the dust storm events is as follows. So I took data from the Iowa Environmental Mesonet website, and I downloaded the NWS METAR WX codes, and I looked for three codes in particular: the BLDU, which is blowing dust; DS, which is dust storms; and DU, which is widespread dust. The latter codes read one of these three codes. I classified it as a dust storm event and then labeled that day as a dust storm day. Then I determined the cause of each dust storm, either convective or synoptic, based on those area forecast discussion reports and those key terms that I mentioned, as well as the now PSR, or short-term forecast reports, that sort of provided a better now sort of forecast of what dust storms were going on. And finally, I analyzed the particulate matter, so the PM10 and PM2.5 concentrations in the atmosphere. And this was essentially used to just corroborate the dust storm events that I identified earlier, to sort of understand and take place that these dust storm events did occur. Here is a yearly distribution of dust storm days from the years 2005 through 2018. In total, there were 471 dust storm days, with an average of about 33 per year, with a standard deviation of 10.7. The maximum number of dust storm days was 49 in 2007, and the minimum was 17 in 2010. So there's certainly some considerable variation here based annually, and future projects of mine will include trying to correlate the incidences of El Nino and La Nina in regards to this trend. Here's a monthly distribution of the dust storm days, and as you can see right away, jumps out at you at the page. The summer months, July, August, and September, are the most common for dust storm events in the Maricopa County area. This is correlated with the monsoon season. So the monsoon season occurs during this time in the state of Arizona, and it generates these convective dust storms that certainly see this really big spike in the number of dust storm events. And this was actually touched on by Dr. Gill a bit earlier. And in regards to the least active months, this is during the winter months, so November through February. And you can certainly see there's a great distribution. The minimum is 8 in January, whereas the maximum is 117 in July. Here, finally, is an hourly distribution of the dust storm days. So clearly, the dust storm events lasting 1 hour were the most common at 60%. And the majority of these dust storm events lasting 1 hour were convective in nature. So they were very quick, they moved through the area, but they were also very intense, as mentioned earlier. These 95% of the dust storm events lasted between 1 through 5 hours, and only very few number of dust storm events lasted 10 hours or more. And the majority, or almost all of these events, were synoptic in nature. So less intensity of the dust storm, but certainly for a more prolonged duration. Here is the hourly distribution of dust storm days by month. The graphs on the right, there are 12 graphs here shown by the month. The y-axis is actually scaled so that you can see sort of the summer months having, again, the most amount of dust storm events. July, August, and September. The month of July had both the greatest number of dust. January and December were the only months to not have a dust storm event lasting longer than 2 hours. Dust storm causes overall, of the 471 dust storm events, the majority, 65%, were convective. These convective events typically had occurred during the late afternoon or evening hours when these convective currents in the atmosphere from the heat generated by the day would cause these thunderstorms to occur. And conversely, 30% were synoptic, and they occurred during all times of the day and the night. There was really no temporal pattern here. 5% had both convective and synoptic. And so this both category right here, these were dust storm events that either were initiated by convective activity and then strengthened by synoptic events, or conversely, initiated by synoptic events and then strengthened by convective activity. So it was difficult to classify which one of the dust storm events, based on the month of the year, as we'll see in a little bit. But for a yearly basis, the sort of spread or distribution of the dust storms stayed fairly constant. Quickly, the July, August, and September months had the greatest number of convective events. And again, this was correlated with the monsoon season here. April actually had the greatest number of synoptic events. So this may be occurring with the spring winds during the season, the associated fronts that roll through. And as well as having the most convective events, July and August had the fewest number of synoptic events. And finally, January had the fewest number of convective events, owing to maybe the lack of heat during these months. And several months, again, as I said earlier, there's really no correlation between the both, but several months do not have any recorded both events. This is a more better representation of sort of how the synoptic and convective trends by month. So December through April, really you can see the majority of the dust storm events that occurred during this time period were synoptic in nature, as in comparison to the summer months, which July, August, September, and October have a greater percentage of convective dust storms. Again, there was really no consistent trend regarding the seasonality, but the timing of the monsoon season, again, is clearly evident for this distribution pattern. Finally, I analyzed the PM10 yearly average distribution versus the dust day distribution. So the dust day distribution is only the dust day events that I identified, and the annual PM10 daily average is that of all of the days in the year. And as you can see for the PM10, there's certainly a major major difference between the two. So the dust storm events certainly had an increase in PM10 concentration, thereby indicating that the dust storm events had occurred, in comparison to the PM2.5, where we really don't see a correlation between, or a difference between, the annual and the dust day average, suggesting that dust storms in the Arizona area are primarily composed of larger, or PM10, particulate matter in comparison to the PM2.5. In conclusion, the dust storm event spread was primarily convective, while only 30% were synoptic. The monsoon season, again, is responsible for the most active months of the year being convective. 95% of the dust storms were very quick, were significantly higher, corroborating my dust event identification. And finally, it's important for us to understand the duration and the seasonal variation of these dust storms to help us predict when they will occur and to allow us to mitigate a lot of their negative impacts. And that concludes my presentation.
Thank you for that, Theodore. Just had one comment in the chat, was just giving you props for a very nice climatological breakdown of the data with good graphics. I think it was good seeing a different perspective outside of West Texas, how things may be a little different. I think it looks like y'all have more, or the Arizona area has more synoptic events than the convective events. And I remember in one presentation it looked like the majority of the ones in West Texas were convective. So that was interesting detail. But with that, we thank you for your presentation. And for those still with us, we still have most of you with us. We're going to transition into lunch. One announcement that we wanted, wanted to make is if you have any need for continuing education credits, either NWA, AMS, or floodplain manager, whatever, one of those three, email the conference and let us know you were watching this morning, or let us know how much you watched throughout these next 2 days, and we'll be able to email you a certificate for that, so you can get credit for those continuing education credits. With that, we're going to go to lunch. We are due back at 1 p.m. Remember, I'm going to go ahead and shut down this stream so that way the computer gets a break and the internet connection gets a break. And so it'll be a new link and a new stream, but you should be able to get to it the same way you did this morning by going to our YouTube channel with the link that we sent out. And once we're live, that new stream should be on that YouTube channel. So we'll meet you back in that new stream at about 1 o'clock. We'll get started right at 1 o'clock. So everyone have a good lunch. We thank you for this joining us this morning. We're thankful that we had a very minimal technical issues, and we hope that trend will continue this afternoon. With that, have a good break.